Book 8, chapters 4 to 6 of 10 books on architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitrúvio, translated by Morris Hickey Morgan. Chapter 4. Tests of good water. 1. Springs should be tested and proved in advance in the following ways. If they run free and open, inspect and observe the physique of the people who dwell in the vicinity before beginning to conduct the water, and if their frames are strong, their complexions fresh, legs sound, and eyes clear, the springs deserve complete approval. If it is a spring just dug out, its water is excellent if it can be sprinkled into a Corinthian vase or into any other sort made of good bronze without leaving a spot on it. Again, if such water is boiled in a bronze cauldron, afterwards left for a time, and then poured off without sand or mud being found at the bottom of the cauldron, that water also will have proved its excellence. 2. And if green vegetables cook quickly when put into a vessel of such water and set over fire, it will be a proof that the water is good and wholesome. Likewise, if the water in the spring is itself limpid and clear, if there is no growth of moss or reeds where it spreads and flows, and if its bed is not polluted by filth of any sort but has a clean appearance, these signs indicate that the water is light and wholesome in the highest degree. Chapter 5. Levelling and levelling instruments. 1. I shall now treat of the ways in which water should be conducted to dwellings and cities. First comes the method of taking the level. Levelling is done either with dioptry, or with water levels, or with the chorobates, but it is done with great accuracy by means of the chorobates because dioptry and levels are deceptive. The chorobates is a straight edge about 20 feet long. At the extremities it has legs, made exactly alike and jointed on perpendicularly to the extremities of the straight edge, and also crosspieces fastened by tenons connecting the straight edge and the legs. These crosspieces have vertical lines drawn upon them, and there are plumb lines hanging from the straight edge over each of the lines. When the straight edge is in position and the plumb lines strike both the lines alike and at the same time, they show that the instrument stands level. 2. But if the wind interposes and constant motion prevents any definite indication by the lines, then have a groove on the upper side 5 feet long, 1 digit wide, and a digit and a half deep, and pour water into it. If the water comes up uniformly to the rims of the groove, it will be known that the instrument is level. When the level is thus found by the means of the chorobates, the amount of fall will also be known. 3. Perhaps some reader of the works of Archimedes will say that there can be no true levelling by means of water, because he holds that water has not a level surface, but is of a spherical form, having its centre at the centre of the earth. Still, whether water is plane or spherical, it necessarily follows that when the straight edge is level, it will support the water evenly at its extremities on the right and left, but that it slopes down at one end, the water at the higher end will not reach the rim of the groove in the straight edge. For though the water, wherever poured in, must have a swelling and curvature in the centre, yet the extremities on the right and left must be on a level with each other. A picture of the chorobates will be found drawn at the end of the book. If there is to be a considerable fall, the conducting of the water will be comparatively easy. But if the course is broken by depressions, we must have recourse to substructures. Chapter 6. Aqueducts, wells, and cisterns. 1. There are 3 methods of conducting water: in channels through masonry conduits, or in lead pipes, or in pipes of baked clay. If in conduits, let the masonry be as solid as possible, and let the bed of the channel have a gradient of not less than 1/4 of an inch for every 100 feet, and let the masonry structure be arched over, so that the sun may not strike the water at all. When it has reached the city, build a reservoir with a distribution tank and 3 compartments connected with the reservoir to receive the water, and let the reservoir have 3 pipes, 1 for each of the connecting tanks, so that when the water runs over from the tanks at the ends, it may run into the one between them. 2. From this central tank, pipes will be laid to all the basins and fountains. from the second tank to baths so that they may yield an annual income to the state, and from the third to private houses so that water for public use will not run short, for people will be unable to divert it if they have only their own supplies from headquarters. This is the reason why I have made these divisions, and also in order that individuals who take water into their houses may by their taxes help to maintain the conducting of the water by the contractors. 3. If, however, there are hills between the city and the source of supply, subterranean channels must be dug and brought to a level at the gradient mentioned above. If the bed is of tufa or other stone, let the channel be cut in it, but if it is of earth or sand, there must be a vaulted masonry walls for the channel, and if the water should thus be conducted, with shafts built at every 240 feet. 4. But if the water is to be conducted in lead pipes, first build a reservoir at the source, then let the pipes have an interior area corresponding to the amount of water, and lay these pipes from this reservoir to the reservoir which is inside the city walls. The pipes should be cast in lengths of at least 10 feet. If they are hundreds, they should weigh 1,200 pounds each length. If 80s, 960 pounds, if 50s, 600 pounds, 40s, 480 pounds, 30s, 360 pounds, 20s, 240 pounds, 15s, 180 pounds, 10s, 120 pounds, 8s, 100 pounds, 5s, 60 pounds. The pipes get the names of their sizes from the width of the plates, taken in digits, before they are rolled into tubes. Thus, when a pipe is made from a plate 50 digits in width, it will be called a 50, and so on with the rest. 5. The conducting of the water through lead pipes is to be managed as follows. If there is regular fall from the source to the city, without any intervening hills that are high enough to interrupt it, but with depressions in it, then we must build substructures to bring it up to the level as in the case of channels and conduits. If the distance round such depressions is not great, the water may be carried round circuitously, but if the valleys are extensive, the course will be directed down their slope. On reaching the bottom, a low substructure is built so that the level there may continue as long as possible. This will form the venter, termed koilia by the Greeks. Then on reaching the hill on the opposite side, the length of the venter makes the water slow in swelling up to rise to the top of the hill. 6. But if there is no such venter made in the valleys, nor any substructure built on a level, but merely an elbow, the water will break out and burst the joints of the pipes, and in the venter, water cushions must be constructed to relieve the pressure of the air. Thus, those who have to conduct water through lead pipes will do it most successfully on these principles, because its descents, circuits, venters, and risings can be managed in this way, when the level of the fall from the sources to the city is once obtained. 7. It is also not ineffectual to build reservoirs at intervals of 24,000 feet, so that if a break occurs anywhere, it will not completely ruin the whole work, and the place where it has occurred can easily be found. But such reservoirs should not be built at a descent, nor in the plane of a venter, nor at risings, nor anywhere in valleys, but only where there is an unbroken level. 8. But if we wish to spend less money, we must proceed as follows. Clay pipes with a skin at least 2 digits thick should be made, but these pipes should be tongued at one end so that they can fit into and join one another. Their joints must be coated with quicklime mixed with oil, and at the angles at the level of the venter a piece of red tufa stone, with a hole bored through it, must be placed right at the elbow, so that the last length of pipe used in the descent is jointed into the stone, and also the first length of the level of the venter. Similarly, at the hill on the opposite side, the last length of the level of the venter should stick into the hole in the red tufa, and the first of the rise should be similarly jointed into it. 9. The level of the pipes being thus adjusted, they will not be sprung out of place by the force generated at the descent and at the rising. For a strong current of air is generated in an aqueduct which bursts its way even through stones, unless the water is let in slowly and sparingly from the source at first, and checked at the elbows or turns by bands, or by the weight of sand ballast. All the other arrangements should be made as in the case of lead pipes, and ashes are to be put in beforehand when the water is let in from the source for the first time, so that if any of the joints have not been sufficiently coated, they may be coated with ashes. 10. Clay pipes for conducting water have the following advantages. In the first place, in construction, if anything happens to them, anybody can repair the damage. Secondly, water from clay pipes is much more wholesome than that which is conducted through lead pipes, because lead is found to be harmful for the reason that white lead is derived from it, and this is said to be hurtful to the human system. Hence, if what is produced from it is harmful, no doubt the thing itself is not wholesome. 11. This we can exemplify from plumbers, since in them the natural colours of the body is replaced by a deep pallor. For when lead is smelted in casting, the fumes from it settle upon their members, and day after day burn out and take away all the virtues of the blood from their limbs. Hence, water ought by no means to be conducted in lead pipes, if we want to have it wholesome. That the taste is better when it comes from clay pipes may be proved by everyday life, for though our tables are loaded with silver vessels, yet everybody uses earthenware for the sake of purity of taste. 12. But if there are no springs from which we can construct aqueducts, it is necessary to dig wells. Now, in the digging of wells we must not disdain reflection, but must devote much acuteness and skill to the consideration of the natural principles of things, because the earth contains many various substances in itself. For like everything else, it is composed of the four elements. In the first place, it is itself earthy, and of moisture it contains springs of water, also heat, which produces sulphur, alum, and asphalt, and finally it contains great currents of air, which coming up in a pregnant state through the porous fissures to the places where wells are being dug, and finding men engaged in digging there, stop up the breath of life in their nostrils by the natural strength of the exhalation. So those who do not quickly escape from the spot are killed there. 13. To guard against this, we must proceed as follows. Let down a lighted lamp, and if it keeps on burning, a man may make the descent without danger. But if the light is put out by the strength of the exhalation, then dig air shafts beside the well on the right and left. Thus the vapours will be carried off by the air shafts as if through nostrils. When these are finished and we come to the water, then a wall should be built round the well without stopping up the vein. 14. But if the ground is hard, or if the veins lie too deep, the water supply must be obtained from roofs or higher ground, and collected in cisterns of signinum work. Signinum work is made as follows. In the first place, procure the cleanest and sharpest sand. Break up lava into bits of not more than a pound in weight, and mix the sand in a mortar trough with the strongest lime in the proportion of 5 parts of sands to 2 of lime. The trench for the signinum work, down to the level of the proposed depth of the cistern, should be beaten with wooden beetles covered with iron. 15. Then, after having beaten the walls, let all the earth between them be cleared out to a level with the very bottom of the walls. Having evened this off, let the ground be beaten to the proper density. If such constructions are in 2 compartments or in 3, so as to ensure clearing by changing from one to another, they will make the water much more wholesome and sweeter to use. For it will become more limpid and keep its taste without any smell, if the mud has somewhere to settle. Otherwise it will be necessary to clear it by adding salt. In this book I have put what I could about the merits and varieties of water, its usefulness, and the ways in which it should be conducted and tested. In the next I shall write about the subject of dialing and the principles of timepieces. End of Book 8. Book 9 of 10 books on architecture. Introduction. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 Books on Architecture by Vitrúvio, translated by Morris Hickey Morgan. Book 9. Introduction. 1. The ancestors of the Greek have appointed such great honours for the famous athletes who are victorious at the Olympian, Pythian, Isthmian, and Nemean games, that they are not only greeted with applause as they stand with palm and crown at the meeting itself, but even on returning to their several states in the triumph of victory, they ride into their cities and to their fathers' houses in 4-horse chariots, and enjoy fixed revenues for life at the public expense. When I think of this, I am amazed that the same honours and even greater are not bestowed upon those authors whose boundless services are performed for all time and for all nations. This would have been a practice all the more worth establishing, because in the case of athletes it is merely their own bodily frame that is strengthened by their training, whereas in the case of authors it is the mind, and not only their own but also man's in general, by the doctrines laid down in their books for the acquiring of knowledge and the sharpening of the intellect. 2. What does it signify to mankind that Milo of Croton and other victors of his class were invincible? Nothing, save that in their lifetime they were famous among their countrymen. But the doctrines of Pythagoras, Democritus, Plato, and Aristotle, in the daily life of other learned men, spent in constant industry, yield fresh and rich fruit not only to their own countrymen but also to all nations, and they who from their tender years are filled with plenteous learning which this fruit affords attain to the highest capacity of knowledge, and can introduce into the states civilized ways, impartial justice, and laws, things without which no state can be sound. 3. Since, therefore, these great benefits to individuals and to communities are due to the wisdom of authors, I think that not only should palms and crowns be bestowed upon them, but that they should even be granted triumphs and judged worthy of being consecrated in the dwellings of the gods. Of their many discoveries which have been useful for the development of human life, I will cite a few examples. On reviewing these, people will admit that honours ought of necessity to be bestowed upon them. 4. First of all, among the many very useful theorems of Plato, I will cite one as demonstrated by him. Suppose there is a place or a field in the form of a square, and we are required to double it. This has to be effected by means of lines correctly drawn, for it will take a kind of calculations not to be made by means of a mere multiplication. The following is the demonstration. A square place 10 feet long and 10 feet wide gives an area of 100 feet. Now, if it is required to double the square and to make one of 200 feet, we must ask how long will be the side of that square so as to get from this the 200 feet corresponding to the doubling of the area. Nobody can find this by means of arithmetic, for if we take 14, multiplication will give 196 feet, if 15, 225 feet. 5. Therefore, since this is inexplicable by arithmetic, let a diagonal line be drawn from angle to angle of that square of 10 feet in length and width, dividing it into 2 triangles of equal size, each 50 feet in area. Taking this diagonal line as the length, describe another square. Thus we shall have in the larger square 4 triangles of the same size and the same number of feet as the 2 of 50 feet each, which were formed by the diagonal line in the smaller square. In this way Plato demonstrated the doubling by means of lines, as the figure appended at the bottom of the page will show. 6. Then again, Pythagoras showed that a right angle can be formed without the contrivances of the artisan. Thus, the result which carpenters reach very laboriously, but scarcely to exactness, with their squares, can be demonstrated to perfection from the reasoning and methods of his teaching. If we take 3 rules, one 3 feet, the second 4 feet, and the third 5 feet in length, and join these rules together with their tips touching each other so as to make a triangular figure, they will form a right angle. Now, if a square be described on the length of each one of these rules, the square on the side of 3 feet in length will have an area of 9 feet, of 4 feet 16, of 5 25. 7. Thus the area in number of feet made up of 2 squares on the sides 3 and 4 feet in length is equalled by that of the 1 square described on the side of 5. When Pythagoras discovered this fact, he had no doubt that the Muses had guided him in the discovery, and it is said that he very gratefully offered sacrifice to them. This theorem affords a useful means of measuring many things, and it is particularly serviceable in the building of staircases in buildings, so that the steps may be at the proper levels. 8. Suppose the height of the story, from the flooring above to the ground below, to be divided into 3 parts. 5 of these will give the right length for the stringers of the stairway. Let 4 parts, each equal to one of the 3, composing the height between the upper story and the ground, be set off from the perpendicular, and there fix the lower ends of the stringers. In this manner the steps and the stairway itself will be properly placed. A figure of this also will be found appended below. 9. In the case of Archimedes, although he made many wonderful discoveries of diverse kinds, yet of them all the following, which I shall relate, seems to have been the result of a boundless ingenuity. Hero, after gaining the royal power in Syracuse, resolved, as a consequence of his successful exploits, to place in a certain temple a golden crown which he had vowed to the immortal gods. He contracted for its making at a fixed price, and weighed out a precise amount of gold to the contractor. At the appointed time the latter delivered to the king's satisfaction an exquisitely finished piece of handiwork, and it appeared that in weight the crown corresponded precisely to what the gold had weighed. 10. But afterwards a charge was made that gold had been abstracted, and an equivalent weight of silver had been added in the manufacture of the crown. Hero, thinking it an outrage that he had been tricked, and yet not knowing how to detect the theft, requested Archimedes to consider the matter. The latter, while the case was still on his mind, happened to go to the bath, and on getting into a tub observed that the more his body sank into it, the more water ran out over the tub. As this pointed out the way to explain the case in question, without a moment's delay and transported with joy, he jumped out of the tub and rushed home naked, crying with a loud voice that he had found what he was seeking. For as he ran he shouted repeatedly in Greek, Eureka, Eureka. 11. Taking this as the beginning of his discovery, it is said that he made 2 masses of the same weight as the crown, one of gold and the other of silver. After making them, he filled a large vessel with water to the very brim, and dropped the mass of silver into it. As much water ran out as was equal in bulk to that of the silver sunk in the vessel. Then, taking up the mass, he poured back the lost quantity of water, using a pint measure, until it was level with the brim as it had been before. Thus he found the weight of silver corresponding to a definite quantity of water. 12. After this experiment he likewise dropped the mass of gold into the full vessel, and, on taking it out and measuring as before, found that not so much water was lost, but a smaller quantity, namely as much less as a mass of gold lacks in bulk compared to a mass of silver of the same weight. Finally, filling the vessel again and dropping the crown itself into the same quantity of water, he found that more water ran over for the crown than for the mass of gold of the same weight. Hence, reasoning from the fact that more water was lost in the case of the crown than in that of the mass, he detected the mixing of silver with the gold, and made the theft of the contractor perfectly clear. 13. Now let us turn our thoughts to the researches of Archytas of Tarentum and Eratosthenes of Cyrene. They made many discoveries from mathematics which are welcome to men, and so, though they deserve our thanks for other discoveries, they are particularly worthy of admiration for their ideas in that field. For example, each in a different way solved the problem enjoined upon Delos by Apollo in an oracle, the doubling of the number of cubic feet in his altars. This done, he said, the inhabitants of the island would be delivered from an offence against religion. 14. Archytas solved it by his figure of the semi-cylinders, Eratosthenes by means of the instrument called mesolabe. Noting all these things with the great delight which learning gives, we cannot but be stirred by these discoveries when we reflect upon the influence of them one by one. I find also much for admiration in the books of Democritus on nature, and in his commentary entitled Keirakmeta, in which he made use of his ring to seal with soft wax the principles which he had himself put to the test. 15. These, then, were men whose researches are an everlasting possession not only for the improvement of character but also for general utility. The fame of athletes, however, soon declines with their bodily powers, neither when they are in the flower of their strength, nor afterwards with posterity can they do for human life which is done by the researches of the learned. 16. But although honours are not bestowed upon authors for excellence of character and teaching, yet as their minds, naturally looking up to the higher regions of the air, are raised to the sky on the steps of history, it must needs be that not merely their doctrines but even their appearance should be known to posterity through time eternal. Hence, men whose souls are aroused by the delights of literature cannot but carry enshrined in their hearts the likeness of the poet Ennius, as they do those of the gods. Those who are devotedly attached to the poems of Accius seem to have before them not merely his vigorous language but even his very figure. 17. So, too, numbers born after our time will feel as if they were discussing nature face to face with Lucretius, or the art of rhetoric with Cicero. Many of our posterity will confer with Varro on the Latin language. Likewise, there will be numerous scholars who, as they weigh many points with the wise among the Greeks, will feel as if they were carrying on private conversations with them. In a word, the opinions of learned authors, though their bodily forms are absent, gain strength as the time goes on, and, when taking part in councils and discussions, have greater weight than those of any living man. 18. Such, Caesar, are the authorities on whom I have depended, and applying their views and opinions, I have written the present books, in the first 7 treating of buildings, and in the 8th of water. In this I shall set forth the rules for dialling, showing how they are found through the shadows cast by the gnomon from the sun's rays in the firmament, and on what principles these shadows lengthen and shorten. End of Book 9. Introduction. Book 9, chapters 1 to 2 of 10 books on architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitrúvio, translated by Morris Hickey Morgan. Chapter 1. The Zodiac and the Planets. 1. It is due to the divine intelligence, and is a very great wonder to all who reflect upon it, that the shadow of a gnomon at the equinox is of one length in Athens, and of another in Alexandria, of another in Rome, and not the same at Piacenza or at other places in the world. Hence drawings for dials are very different from one another, corresponding to the differences of situation. This is because the length of the shadow at the equinox is used in constructing the figure of the analemma, in accordance with which the hours are marked to conform to the situation and the shadow of the gnomon. The analemma is a basis for calculation deduced from the course of the sun and found by observation of the shadow as it increases until the winter solstice. By means of this, through architectural principles and the employment of the compasses, we find out the operation of the sun in the universe. 2. The word universe means the general assemblage of all nature, and it also means the heaven that is made up of the constellation and the courses of the stars. The heaven revolves steadily round earth and sea on the pivots at the ends of its axis. The architect at these points was the power of nature, and she put the pivots there to be, as it were, centres, one of them above the earth and sea at the very top of the firmament, and even beyond the stars composing the Great Bear, the other on the opposite side under the earth in the regions of the south. Round these pivots, termed in Greek poloi, as centres, like those of turning lathe, she formed the circles into which the heaven passes on its everlasting way. In the midst thereof the earth and sea naturally occupy the central point. 3. It follows from this natural arrangement that the central point in the north is high above the earth, while on the south, the region below, it is beneath the earth and consequently hidden by it. Furthermore, across the middle, and obliquely inclined to the south, there is a broad circular belt composed of the 12 signs, whose stars, arranged in 12 equivalent divisions, represent each a shape which nature has depicted. And so with the firmament and the other constellations, they move round the earth and sea in glittering array, completing their orbits according to the spherical shape of the heaven. 4. They are all visible or invisible according to fixed times. While 6 of the signs are passing along with the heaven above the earth, the other 6 are moving under the earth and hidden by its shadow. But there are always 6 of them making their way above the earth, for corresponding to that part of the last sign which in the course of its revolution has to sink, pass under the earth, and become concealed, an equivalent part of the sign opposite to it is obliged by the law of their common revolution to pass up and, having completed its circuit, to emerge out of the darkness into the light of the open space on the other side. This is because the rising and setting of both are subject to one and the same power and law. 5. While these signs, 12 in number and occupying each 1/12th part of the firmament, steadily revolve from east to west, the moon, Mercury, Venus, the sun, as well as Mars, Jupiter, and Saturn, differing from one another in the magnitude of their orbits, as though their courses were at different points in a flight of steps, pass through those signs in just the opposite direction, from west to east in the firmament. The moon makes her circuit of the heaven in 28 days plus about an hour, and with her return to the sign from which she set forth completes a lunar month. 6. The sun takes a full month to move across the space of one sign, that is, 1/12 of the firmament. Consequently, in 12 months she traverses the spaces of the 12 signs, and, on returning to the sign from which he began, completes the period of a full year. Hence, the circuit made by the moon 13 times in 12 months is measured by the sun only once in the same number of months. But Mercury and Venus, their paths wreathing around the sun's rays as their centre, retrograde and delay their movements, and so, from the nature of that circuit, sometimes wait at stopping places within the spaces of the signs. 7. This fact may best be recognized from Venus. When she is following the sun, she makes her appearance in the sky after his setting, and is then called the evening star, shining most brilliantly. At other times she precedes him, rising before daybreak, and is named the morning star. Thus Mercury and Venus sometimes delay in one sign for a good many days, and at others advance pretty rapidly into another sign. They do not spend the same number of days in every sign, but the longer they have previously delayed, the more rapidly they accomplish their journeys after passing into the next sign, and thus they complete their appointed course. Consequently, in spite of their delay in some of the signs, they nevertheless soon reach the proper place in their orbits after freeing themselves from their enforced delay. 8. Mercury, on his journey through the heavens, passes through the spaces of the signs in 360 days, and so arrives at the sign from which he set out on his course at the beginning of his revolution. His average rate of movement is such that he has about 30 days in each sign. 9. Venus, on becoming free from the hindrance of the sun's rays, crosses the space of a sign in 30 days. Though she thus stays less than 40 days in particular signs, she makes good the required amount by delaying in one sign when she comes to a pause. Therefore she completes her total revolution in heaven in 485 days, and once more enters the sign from which she previously began to move. 10. Mars, after traversing the spaces of the constellation for about 683 days, arrives at the point from which he had before set out at the beginning of his course, and while he passes through some of the signs more rapidly than others, he makes up the required number of days whenever he comes to a pause. Jupiter, climbing with gentler pace against the revolution of the firmament, travels through each sign in about 360 days, and finishes in 11 years and 313 days, returning to the sign in which he had been 12 years before. Saturn, traversing the space of one sign in 29 months plus a few days, is restored after 29 years, and about 160 days to that in which he had been 30 years before. He is, as it appears, slower, because the nearer he is to the outermost part of the firmament, the greater is the orbit through which he has to pass. 11. The three that complete their circuits above the sun's course do not make progress while they are in the triangle which he has entered, but retrograde and pause until the sun has crossed from that triangle into another sign. Some hold that this takes place because, as they say, when the sun is a great distance off, the paths on which these stars wander are without light on account of that distance, and so the darkness retards and hinders them. But I do not think that this is so. The splendor of the sun is clearly to be seen, and manifest without any kind of obscurity, throughout the whole firmament, so that those very retrograde movements and pauses of the stars are visible even to us. 12. If then, at this great distance, our human vision can discern that sight, why, pray, are we to think that the divine splendor of the stars can be cast into darkness? Rather will the following way of accounting for it prove to be correct. Heat summons and attracts everything towards itself. For instance, we see the fruits of the earth growing up high under the influence of heat, and that spring water is vaporized and drawn up on the clouds at sunrise. On the same principle, the mighty influence of the sun, with its rays diverging in the form of a triangle, attracts the stars which follow him, and, as it were, curbs and restrains those that precede, not allowing them to make progress, but obliging them to retrograde towards himself until he passes out into the sign that belongs to a different triangle. 13. Perhaps the question will be raised, why the sun by his great heat causes these detentions in the fifth sign from himself rather than in the second or third, which are nearer. I will therefore set forth what seems to be the reason. His rays diverging through the firmament in straight lines, as though forming an equilateral triangle, that is, to the fifth sign from the sun, no more, no less. If his rays were diffused in circuits spreading all over the firmament instead of in straight lines diverging so as to form a triangle, they would burn up all the nearer objects. This is a fact which the Greek poet Euripides seems to have remarked, for he says that places at a greater distance from the sun are in violent heat, and that those which are nearer he keeps temperate. Thus in the play of Phaethon the poet writes, kai ei taporo tangythen dev ekrat ekei. 14. If then fact and reason and the evidence of an ancient poet point to this explanation, I do not see why we should decide otherwise than as I have written above on this subject. Jupiter, whose orbit is between those of Mars and Saturn, traverses a longer course than Mars and a shorter than Saturn. Likewise, with the rest of these stars, the farther they are from the outermost limits of the heaven, and the nearer their orbits to the earth, the sooner they are seen to finish their courses, for those of them that have a smaller orbit often pass those that are higher, going under them. 15. For example, place 7 ants on a wheel such as potters use, having made 7 channels on the wheel about the center, increasing successively in circumference, and suppose those ants obliged to make a circuit in these channels while the wheel is turned in the opposite direction. In spite of having to move in a direction contrary to that of the wheel, the ants must necessarily complete their journeys in the opposite direction, and that ant which is nearest the center must finish its circuit sooner, while the ant that is going round at the outer edge of the disc of the wheel must, on account of the size of its circuit, be much slower in completing its course, even though it is moving just as quickly as the other. In the same way, these stars which struggle on against the course of the firmament are accomplishing an orbit on paths of their own, but, owing to the revolution of the heaven, they are swept back as it goes round every day. 16. The reason why some of these stars are temperate, others hot, and others cold, appears to be this, that the flame of every kind of fire rises to higher places. Consequently, the burning rays of the sun make the ether above him white hot in the regions of the course of Mars, and so the heat of the sun makes him hot. Saturn, on the contrary, being nearest to the outermost limit of the firmament and bordering on the quarters of the heaven which are frozen, is excessively cold. Hence, Jupiter, whose course is between the orbits of these two, appears to have a moderate and very temperate influence, intermediate between their cold and heat. I have now described, as I have received them from my teacher, the belt of the 12 signs and the 7 stars that work and move in the opposite direction, with the laws and numerical relations under which they pass from sign to sign, and how they complete their orbits. I shall next speak of the waxing and waning of the moon, according to the accounts of my predecessors. Chapter 2. The phases of the moon. 1. According to the teaching of Berosus, who came from the state, or rather nation, of the Chaldees, and was the pioneer of Chaldean learning in Asia, the moon is a ball, one half luminous and the rest of a blue color. When, in the course of her orbit, she has passed below the disk of the sun, she is attracted by his rays in great heat, and turns thither her luminous side, on account of the sympathy between light and light. Being thus summoned by the sun's disk, and facing upward, her lower half, as it is not luminous, is invisible on account of the likeness to the air. When she is perpendicular to the sun's rays, all her light is confined to her upper surface, and she is then called the new moon. 2. As she moves on, passing by to the east, the effect of the sun upon her relaxes, and the outer edge of the luminous side sheds its light upon the earth in an exceedingly thin line. This is called the second day of the moon. Day by day she is further relieved and turns, and thus are numbered the 3rd, 4th, and following days. On the 7th day, the sun being in the west and the moon in the middle of the firmament between the east and west, she is half the extent of the firmament distant from the sun, and therefore half of the luminous side is turned toward the earth. But when the sun and moon are separate by the entire extent of the firmament, and the moon is in the east with the sun over against her in the west, she is completely relieved by her still greater distance from his rays, and so on the 14th day she is at the full, and her entire disk emits its light. On the succeeding days, up to the end of the month, she wanes daily as she turns in her course, being recalled by the sun until she comes under his disk and rays, thus completing the count of the days of the month. 3. But Aristarchus of Samos, a mathematician of great powers, has left a different explanation in his teaching on this subject, as I shall now set forth. It is no secret that the moon has no light of her own, but is, as it were, a mirror, receiving brightness from the influence of the sun. Of all the 7 stars, the moon traverses the shortest orbit, and her course is nearest to the earth. Hence, in every month, on the day before she gets past the sun, she is under the disk and rays, and is consequently hidden and invisible. When she is thus in conjunction with the sun, she is called the new moon. On the next day, reckoned as her second, she gets past the sun and shows the thin edge of her sphere. 3 days away from the sun she waxes and grows brighter, removing further every day till she reaches the 7th, when her distance from the sun at his setting is about 1/2 the extent of the firmament. 1/2 of her is luminous, that is, the half which faces toward the sun is lighted up by him. 4. On the 14th day, being diametrically across the whole extent of the firmament from the sun, she is at her full, and rises when the sun is setting. For, as she takes her place over against him and distant to the whole extent of the firmament, she thus receives the light from the sun throughout her entire orb. On the 17th day, at sunrise, she is inclining to the west. On the 22nd day, after sunrise, the moon is about mid-heaven. Hence, the side exposed to the sun is bright and the rest dark. Continuing thus her daily course, she passes under the rays of the sun on about the 28th day, and so completes the account of the month. I will next explain how the sun, passing through a different sign each month, causes the days and hours to increase and diminish in length. End of Book 9, Chapter 2. Book 9, Chapters 3 to 6 of 10 books on architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitrúvio, translated by Morris Hickey Morgan. Chapter 3. The course of the sun through the 12 signs. 1. The sun, after entering the sign Aries and passing through 1/8 of it, determines the vernal equinox. On reaching the tail of Taurus and the constellation of the Pleiades, from which the front half of the Taurus projects, he advances into a space greater than half the firmament, moving towards the north. From Taurus he enters Gemini at the time of the rising of the Pleiades, and getting higher above the earth, he increases the length of the days. Next, coming from Gemini into Cancer, which occupies the shortest space in heaven, and after traversing 1/8 of it, he determines the summer solstice. Continuing on, he reaches the head and breast of Leo, portions which are reckoned as belonging to Cancer. 2. After leaving the breast of Leo and the boundaries of Cancer, the sun, traversing the rest of Leo, makes the days shorter, diminishing the size of his circuit, and returning to the same course that he had in Gemini. Next, crossing from Leo into Virgo and advancing as far as the bosom of her garment, he still further shortens his circuit, making his course equal to what it was in Taurus. Advancing from Virgo by way of the bosom of her garment, which forms the first part of Libra, he determines the autumn equinox at the end of 1/8 of Libra. Here his course is equal to what his circuit was in the sign Aries. 3. When the sun has entered Scorpio, at the time of the setting of the Pleiades, he begins to make the days shorter as he advances toward the south. From Scorpio he enters Sagittarius, and on reaching the thighs his daily course is still further diminished. From the thighs of Sagittarius, which are reckoned as part of Capricornus, he reaches the end of the first eighth of the latter, where his course in heaven is shortest. Consequently, this season, from the shortness of the day, is called Bruma, or Dies Brumales. Crossing from Capricornus into Aquarius, he causes the days to increase to the length which they had when he was in Sagittarius. From Aquarius he enters Pisces at the time when Favonius begins to blow, and here his course is the same as in Scorpio. In this way the sun passes round through the signs, lengthening or shortening the days and hours at definite seasons. I shall next speak of the other constellations formed by arrangements of stars and lying to the right and left of the belt of the signs, in the southern and northern portion of the firmament. Chapter 4. The Northern Constellations. 1. The Great Bear, called in Greek Arctos, or Helike, has her warden behind her. Near him is the Virgin, on whose right shoulder rests a very bright star which we call the harbinger of the vintage, and the Greeks Protrygetes. But Spica in that constellation is brighter. Opposite there is another star, coloured between the knees of the bear warden, dedicated there under the name of Arcturus. 2. Opposite the head of the bear, at an angle with the feet of the twins, is the charioteer, standing on the tip of the horn of the bull. Hence, one and the same star is found on the tip of the left horn of the bull and in the right foot of the charioteer. Supported on the hand of the charioteer are the kids, with the she-goat at his left shoulder. Above the bull and the ram is Perseus, having at his right, with the Pleiades moving beneath, and at his left the head of the ram. His right hand rests on the likeness of Cassiopeia, and with his left he holds the Gorgon's head by its top over the ram, laying it at the feet of Andromeda. 3. Above Andromeda are the fishes, one above her belly and the other above the backbone of the horse. A very bright star terminates both the belly of the horse and the head of Andromeda. Andromeda's right hand rests above the likeness of Cassiopeia, and her left above the northern fish. The waterman's head is above that of the horse. The horse's hoofs lie close to the waterman's knees. Cassiopeia is set apart in the midst. High above the he-goat are the eagle and the dolphin, and near them is the arrow. Farther on is the bird, whose right wing grazes the head and sceptre of Cepheus, with its left resting over Cassiopeia. Under the tail of the bird lie the feet of the horse. 4. Above the archer, scorpion, and balance is the serpent, reaching to the crown with the end of its snout. Next, the serpent holder grasps the serpent above the middle in his hands, and with his left foot treads squarely on the foreparts of the scorpion. A little way from the head of the serpent holder is the head of the so-called kneeler. Their heads are the more readily to be distinguished, as the stars which compose them are by no means dim. 5. The foot of the kneeler rests on the temple of the serpent which is entwined between the she-bears, called septentrionus. The little dolphin moves in front of the horse. Opposite the bill of the bird is the lyre. The crown is arranged between the shoulders of the warden and the kneeler. In the northern circle are the two she-bears with their shoulder blades confronting and their breasts turned away from one another. The Greeks called the lesser bear Konosaura and the greater Elike. Their heads face different ways, and their tails are shaped so that each is in front of the head of the other bear, for the tails of both stick up over them. 6. The serpent is said to lie stretched out between their tails, and in it there is a star, called Polus, shining near the head of the greater bear. At the nearest point, the serpent winds its head round, but is also flung in a fold round the head of the lesser bear and stretches out close to her feet. Here it twists back, making another fold, and, lifting itself up, bends its note and right temple from the head of the lesser bear round towards the greater. Above the tail of the lesser bear are the feet of Cepheus, and at this point, at the very top, are stars forming an equilateral triangle. There are a good many stars common to the lesser bear and the Cepheus. I have now mentioned the constellations which are arranged in the heaven to the right of the east, between the belt of the signs and the north. I shall next describe those that nature has distributed to the left of the east and the southern regions. Chapter 5. The southern constellations. 1. First, under the he-goat lies the southern fish, facing towards the tail of the whale. The censer is under the scorpion's sting. The foreparts of the cantar are next to the balance and the scorpion, and he holds in his hands the figure which astronomers call the beast. Beneath the virgin, lion, and crab is the twisted girdle formed by the snake, extending over a whole line of stars, his snout raised near the crab, supporting the bowl with the middle of his body near the lion, and bringing his tail, on which is the raven, under and near the hand of the virgin. The region above his shoulders is equally bright. 2. Beneath the snake's belly, at the tail, lies the centaur. Near the bow and the lion is a ship named Argo. Her bow is invisible, but her mast and the parts about the helm are in plain sight, the stern of the vessel joining the dog at the tip of his tail. The little dog follows the twins, and is opposite the snake's head. The greater dog follows the lesser. Orion lies aslant, under the bull's hoof, in his left hand grasping his club, and raising the other towards the twins. 3. At his feet is the dog, following a little behind the hare. The whale lies under the ram and the fishes, and from his mane there is a slight sprinkling of stars, called in Greek harpedonai, regularly disposed towards each of the fishes. This ligature by which they hang is carried a great way inwards, but reaches out to the top of the mane of the whale. The river, formed of stars, flows from a source at the left foot of Orion, but the water, said to pour from the waterman, flows between the head of the southern fish and the tail of the whale. 4. These constellations, whose outlines and shapes in the heavens were designed by nature and the divine intelligence, I have described according to the view of the natural philosopher Democritus, but only those whose rising and settings we can observe and see with our own eyes. Just as the bears turn round the pivot of the axis without ever setting or sinking under the earth, there are likewise stars that keep turning round the southern pivot, which, on account of the inclination of the firmament, lies always under the earth, and being hidden there, they never rise and emerge above the earth. Consequently, the figures which they form are unknown to us on account of the interposition of the earth. The star Canopus proves this. It is unknown to our vicinity, but we have reports of it from merchants who have been to the most distant parts of Egypt, and to regions bordering on the uttermost boundaries of the earth. Chapter 6. Astrology and Weather Prognostics. 1. I have shown how the firmament and the 12 signs with the constellation arranged to the north and south of them fly round the earth, so that the matter may be clearly understood. For it is from this revolution of the firmament, from the course of the sun through the signs in the opposite direction, and from the shadows cast by equinoctial gnomons, that we find the figure of the analemma. 2. As for the branch of astronomy which concerns the influences of 12 signs, the 5 stars, the sun, and the moon upon human life, we must leave all this to the calculations of the Chaldeans, to whom belongs the art of casting nativities, which enables them to declare the past and the future by means of calculations based on the stars. These discoveries have been transmitted by the men of genius and great acuteness who sprang directly from the nations of the Chaldeans. First of all by Berosus, who settled in the island state of Kos, and there opened a school. Afterwards Antipater pursued this subject. Then there was Archinapolis, who also left rules for casting nativities, based not on the moment of birth, but on that of conception. 3. When we come to the natural philosophy, however, Thales of Miletus, Anaxagoras of Clazomenae, Pythagoras of Samos, Xenophanes of Colophon, and Democritus of Abdera have in various ways investigated and left us the laws and the working of the laws by which nature governs it. In the track of their discoveries, Evdoxus, Evctemon, Callippus, Meto, Philippus, Hipparchus, Aratus, and others discovered the risings and settings of the constellations, as well as weather prognostications from astronomy through the study of the calendars, and this study they set forth and left to posterity. Their learning deserves the admiration of mankind, for they were so solicitous as even to be able to predict long beforehand with divining mind the signs of the weather which was to follow in the future. On this subject, therefore, reference must be made to their labours and investigations. End of Book 9, Chapter 6. Book 9, Chapters 7 and 8 of 10 books on architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitrúvio. Translated by Morris Hickey Morgan. Chapter 7. The Analemma and its applications. 1. In distinction from the subjects first mentioned, we must ourselves explain the principles which govern the shortening and lengthening of the day. When the sun is at the equinoxes, that is, passing through Aries or Libra, he makes the gnomon cast a shadow equal to 8/9 of its own length in the latitude of Rome. In Athens the shadow is equal to 3/4 of the length of the gnomon, at Rhodes to 5/7, at Tarentum to 9/11, at Alexandria to 3/5, and so at other places it is found that the shadows of equinoctial gnomons are naturally different from one another. 2. Hence, wherever a sundial is to be constructed, we must take the equinoctial shadow of the place. If it is found to be, as in Rome, equal to 8/9 of the gnomon, let a line be drawn on a plane surface, and in the middle thereof erect a perpendicular, plumb to the line, which perpendicular is called the gnomon. Then, from the line in the plane, let the line of the gnomon be divided off by compasses into 9 parts, and take the point designating the 9th part as a centre to be marked by the letter A. Then, opening the compasses from the centre to the line in the plane at the point B, describe a circle. This circle is called the meridian. 3. Then, on the 9 parts between the plane and the centre of the gnomon, take 8, and mark them off on the line in the plane to the point C. This will be the equinoctial shadow of the gnomon. From that point, marked by C, let a line be drawn through the centre at the point A, and this will represent a ray of the sun at the equinox. Then, extending the compasses from the centre to the line in the plane, mark off the equidistant points E on the left and I on the right on the 2 sides of the circumference, and let a line be drawn through the centre, dividing the circle into 2 equal semicircles. This line is called by mathematicians the horizon. 4. Then, take a 15th part of the entire circumference, and, placing the centre of the compasses on the circumference at the point where the equinoctial ray cuts it at the letter F, mark off the points G and H on the right and left. Then lines must be drawn from these and the centre to the line of the plane at the points T and R, and thus one will represent the ray of the sun in winter and the other the ray in summer. Opposite E will be the point I, where the line drawn through the centre at the point A cuts the circumference. Opposite G and H will be the points L and K, and opposite C, F, and A will be the point N. 5. Then diameters are to be drawn from G to L and from H to K. The upper will denote the summer and the lower the winter portion. These diameters are to be divided equally in the middle at the points M and O and those centers marked. Then, through these marks and the center A, draw a line extending to the two sides of the circumference at the points P and Q. This will be a line perpendicular to the equinoctial ray, and it is called in mathematical figures the axis. From these same centers open the compasses to the ends of the diameters and describe semicircles, one of which will be for summer and the other for winter. 6. Then, at the points at which the parallel lines cut the line called the horizon, the letter S is to be on the right and the letter V on the left, and from the extremity of the semicircle at the point G, draw a line parallel to the axis extending to the left-hand semicircle at the point H. This parallel line is called the logotomus. Then center the compasses at the point where the equinoctial ray cuts that line at the letter D, and open them to the point where the summer ray cuts the circumference at the letter H. From the equinoctial center, with radius extending to the summer ray, describe the circumference of the circle of the months, which is called Menneus. Thus we shall have the figure of the analemma. 7. This having been drawn and completed, the scheme of hours is next to be drawn on the base plates from the analemma, according to the winter lines, or those of summer, or the equinoxes, or the months, and thus many different kinds of dials may be laid down and drawn by this ingenious method. But the result of all these shapes and designs is in one respect the same, namely, the days of the equinoxes and of the winter and summer solstices are always divided into 12 equal parts. Omitting details, therefore, not for fear of the trouble, but lest I should prove tiresome by writing too much, I will state by whom the different classes and designs of dials have been invented. For I cannot invent new kinds myself at this late day, nor do I think that I ought to display the inventions of others as my own. Hence I will mention those that have come down to us and by whom they were invented. Chapter 8. Sundials and Water Clocks. 1. The semicircular form, hollowed out of a square block and cut under to correspond to the polar altitude, is said to have been invented by Berosus the Chaldean. The scaff or hemisphere by Aristarchus of Samos, as well as the disc on a plane surface. The arachne by the astronomer Evdoxus, or, as some say, by Apollonius. The plinthium or lacunar, like the one placed in the Circus Flaminius, by Scopinas of Syracuse. The pros ta historomena by Parmenio, the pros panclima by Theodosius and Andreas, the pelesinum by Patroclus, the cone by Dionysius Dorus, the quiver by Apollonius. The men whose names are written above, as well as many others, have invented and left us other kinds, as, for instance, the conarachne, the conical plinthium, and the antiborean. Many have also left us written directions for making dials of these kinds for travellers, which can be hung up. Whoever wishes to find their base plates can easily do so from the books of these writers, provided only he understands the figure of the analemma. 2. Methods of making water clocks have been investigated by the same writers, and first of all by Ctesibius the Alexandrian, who also discovered the natural pressure of the air and pneumatic principles. It is worthwhile for students to know how these discoveries came about. Ctesibius, born at Alexandria, was the son of a barber. Preeminent for natural ability and great industry, he is said to have amused himself with ingenious devices. For example, wishing to hang a mirror in his father's shop in such a way that, on being lowered and raised again, its weight should be raised by means of a concealed cord, he employed the following mechanical contrivance. 3. Under the roof beam he fixed a wooden channel in which he arranged a block of pulleys. He carried the cord along the channel to the corner, where he set up some small piping. Into this a leaden ball attached to the cord was made to descend. As the weight fell into the narrow limits of the pipe, it naturally compressed the enclosed air, and as its fall was rapid, it forced the mass of compressed air through the outlet into the open air, thus producing a distinct sound by the concussion. 4. Hence, Ctesibius, observing that sounds and tones were produced by the contact between the free air and that which was forced from the pipe, made use of this principle in the construction of the first water organs. He also devised the methods of raising water, automatic contrivances, and amusing things of many kinds, including among them the construction of water clocks. He began by making an orifice in a piece of gold or by perforating a gem, because these substances are not worn by the action of water, and do not collect dirt so as to get stopped up. 5. A regular flow of water through the orifice raises an inverted bowl, called by the mechanicians the cork or drum. To this are attached a rack and a revolving drum, both fitted with teeth at regular intervals. These teeth, acting upon one another, induce a measured revolution and movement. Other racks and other drums, similarly toothed and subject to the same motion, give rise by the revolution to various kinds of motions by which figures are moved, cones revolve, pebbles or eggs fall, trumpets sound, and other incidental effects take place. 6. The hours are marked in these clocks on a column or a pilaster, and a figure emerging from the bottom points to them with a rod throughout the whole day. Their decrease or increase in length with the different days and months must be adjusted by inserting or withdrawing wedges. The shut-offs for regulating the water are constructed as follows. 2 cones are made, one solid and the other hollow, turned on a lathe so that one will go into the other and fit it perfectly. A rod is used to loosen or to bring them together, thus causing the water to flow rapidly or slowly into the vessels. According to these rules and by this mechanism, water clocks may be constructed for use in winter. 7. But it proves that the shortening or lengthening of the day is not in agreement with the insertion and removal of the wedges, because the wedges may very often cause errors. The following arrangement will have to be made. Let the hours be marked off transversely on the column from the analemma, and let the lines of the months also be marked upon the column. Then let the column be made to revolve in such a way that, as it turns continuously towards the figure and the rod with which the emerging figure points to the hours, it may make the hours short or long according to the respective months. 8. There is also another kind of winter dial called the anaphoric and constructed in the following way. The hours, indicated by bronze rods in accordance with the figure of the analemma, radiate from a center on the face. Circles are described upon it, marking the limits of the months. Behind these rods there is a drum, on which is drawn and painted the firmament with the circle of the signs. In drawing the figures of the 12 celestial signs, one is represented larger and the next smaller, proceeding from the center. Into the back of the drum, in the middle, a revolving axis is inserted, and round that axis is wound a flexible bronze chain, at one end at which hangs the cork which is raised by the water, and at the other a counterpoise of sand equal in weight to the cork. 9. Hence the sand sinks as the cork is raised by the water, and in sinking turns the axis, and the axis the drum. The revolution of this drum causes sometimes a larger and sometimes a smaller portion of the circle of the signs to indicate, during the revolution, the proper length of the hours corresponding to their seasons. For in every one of the signs there are as many holes as the corresponding month has days, and a boss, which seems to be holding the representation of the sun on the dial, designates the spaces for the hours. This, as it is carried from hole to hole, completes the circuit of a full month. 10. Hence, just as the sun, during his passage through the constellations, makes the days and hours longer or shorter, so the boss on a dial, moving from point to point in a direction contrary to that of the revolution of the drum in the middle, is carried day by day, sometimes over wider and sometimes over narrower spaces, giving a representation of hours and days within the limits of each month. To manage the water so that it may flow regularly, we must proceed as follows. 11. Inside, behind the face of the dial, place a reservoir, and let the water run down into it through a pipe, and let it have a hole at the bottom. Fastened to it is a bronze drum, with an opening through which the water flows into it from the reservoir. Enclosed in this drum there is a smaller one, the two being perfectly jointed together by tenon and socket, in such a way that the smaller drum revolves closely but easily in the larger, like a stopcock. 12. On the lip of the larger drum there are 365 points, marked off at equal intervals. The rim of the smaller one has a tongue fixed on its circumference with the tip directed towards those points, and also in this rim is a small opening through which water runs into the drum and keeps the works going. The figures of the celestial signs being on the lip of the larger drum, and this drum being motionless, let the sign Cancer be drawn at the top, with Capricornus perpendicular to it at the bottom, Libra at the spectator's right, Aries at his left, and let the other signs be given places between them as they are seen in the heavens. 12. Hence, when the sun is in Capricornus, the tongue on the rim touches every day one of the points in Capricornus on the lip of the large drum, and is perpendicular to the strong pressure of this running water. So the water is quickly driven through the opening in the rim to the inside of the vessel, which, receiving it and soon becoming full, shortens and diminishes the length of the days and hours. But then, owing to the daily revolution of the smaller drum, its tongue reaches the points in Aquarius, the opening will no longer be perpendicular, and the water must give up its vigorous flow and run in a slower stream. Thus, the less velocity with which the vessel receives the water, the more the length of the days is increased. 14. Then the opening in the rim passes from point to point in Aquarius and Pisces as though going upstairs, and when it reaches the end of the first eighth of Aries, the fall of the water is of medium strength, indicating the equinoctial hours. From Aries the opening passes, with the revolution of the drum, through Taurus and Gemini to the highest points at the end of the first eighth of Cancer, and when it reaches that point the power diminishes, and hence, with slower flow, its delay lengthens the days in the sign Cancer, producing the hours of the summer solstice. From Cancer it begins to decline, and during its return it passes through Leo and Virgo to the points at the end of the first eighth of Libra, gradually shortening and diminishing the length of the hours until it comes to the points in Libra, where it makes the hours equinoctial once more. 15. Finally, the opening comes down more rapidly through Scorpio and Sagittarius, and on its return from its revolution to the end of the first eighth of Capricornus, the velocity of the stream renews once more the short hours of the winter solstice. The rules and forms of construction employed in designing dials have now been described as well as I could. It remains to give an account of machines and their principles. In order to make my treatise on architecture complete, I will begin to write on this subject in the following book. End of Book 9. Book 10, Introduction and Chapter 1 of 10 Books on Architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 Books on Architecture by Vitrúvio, translated by Morris Hickey Morgan. Book 10, Introduction. 1. In the famous and important Greek city of Ephesus there is said to be an ancient ancestral law, the terms of which are severe, but its justice is not inequitable. When an architect accepts the charge of a public work, he has to promise what the cost of it will be. His estimate is handed to the magistrate, and his property is pledged as security until the work is done. When it is finished, if the outlay agrees with his statement, he is complimented by decrees and marks of honor. If no more than a fourth has to be added to his estimate, it is furnished by the treasury and no penalty is inflicted. But when more than 1/4 has to be spent in addition on the work, the money required to finish it is taken from his property. 2. Would to God that this were also law of the Roman people, not merely for public but also for private buildings. For the ignorant would no longer run riot with impunity, but men who are well qualified by an exact scientific training would unquestionably adopt the profession of architecture. Gentlemen would not be misled into limitless and prodigal expenditure, even to ejectments from their estates, and the architects themselves could be forced, by fear of the penalty, to be more careful in calculating and stating the limit of expense, so that gentlemen would procure their buildings for that which they had expected, or by adding only a little more. It is true that men who can afford to devote 400,000 to a work may hold on, if they have to add another 100,000, from the pleasure which the hope of finishing it gives them. But if they are loaded with a 50% increase or with an even greater expense, they lose hope, sacrifice what they have already spent, and are compelled to leave off, broken in fortune and in spirit. 3. This fault appears not only in the matter of buildings, but also in the shows given by magistrates, whether of gladiators in the forum or of plays on the stage. Here neither delay nor postponement is permissible, but the necessity of the case required that everything should be ready at a fixed time: the seats for the audience, the awning drawn over them, and whatever, in accordance with the customs of the stage, is provided by machinery to please the eye of the people. These matters require careful thought and planning by a well-trained intellect, for none of them can be accomplished without machinery, and without hard study skilfully applied in various ways. 4. Therefore, since such are our traditions and established practices, it is obviously fitting that the plans should be worked out carefully, and with the greatest attention, before the structures are begun. Consequently, as we have no law or customary practice to compel this, and as every year both praetors and aediles have to provide machinery for the festivals, I have thought it not out of place, Emperor, since I have treated of buildings in the earlier books, to set forth and teach in this, which forms the final conclusion of my treatise, the principles which govern machines. Chapter 1. Machines and Implements. 1. A machine is a combination of timbers fastened together, chiefly efficacious in moving great weights. Such a machine is set in motion on scientific principles in circular rounds, which the Greeks call kyklike kineos. There is, however, a class intended for climbing, termed in Greek akrobatikon, another worked by air, which with them is called pneumatikon, and a third for hoisting, this the Greeks named barolkos. In the climbing class are machines so disposed that one can safely climb up high, by means of timbers set up on end and connected by crossbeams, in order to view operations. In the pneumatic class, air is forced by pressure to produce sounds and tones as in an organon. 2. In the hoisting class, heavy weights are removed by machines which raise them up and set them in position. The climbing machines display no scientific principle, but merely a spirit of daring. It is held together by dowels and crossbeams and twisted lashings and supporting props. A machine that gets its motive power by pneumatic pressure will produce pretty effects by scientific refinements, but the hoisting machine has opportunities for usefulness which are greater and full of grandeur, and it is of the highest efficacy when used with intelligence. 3. Some of these act on the principles of the mechane, others on that of the organon. The difference between machines and engines is obviously this, that machines need more workmen and greater power to make them take effect, as for instance ballistae and the beams of presses. Engines, on the other hand, accomplish their purpose at the intelligent touch of a single workman, as the scorpio or anisocycli when they are turned. Therefore engines, as well as machines, are in principle practical necessities, without which nothing can be unattended with difficulties. 4. All machinery is derived from nature, and is founded on the teaching and instruction of the revolution of the firmament. Let us but consider the connected revolutions of the sun, the moon, and the 5 planets, without the revolution of which, due to mechanism, we should not have had the alternation of day and night, nor the ripening of fruits. Thus, when our ancestors had seen that this was so, they took their models from nature, and by imitating them were led on by divine facts, until they perfected their contrivances which are so serviceable in our life. Some things, with a view to a greater convenience, they worked out by means of machines and their revolutions, others by means of engines, and so whatever they found to be useful for investigations, for the arts, and for the established practices, they took care to improve step by step on scientific principles. 5. Let us first take a necessary invention, such as clothing, and see how the combination of warp and woof on the loom, which does its work on the principle of an engine, not only protects the body by covering it, but also gives it honourable apparel. We should not have food in abundance unless yokes and ploughs for oxen and for all draught animals had been invented. If there had been no provision of windlasses, press beams, and levers for presses, we could not have had the shining oil, nor the fruit of the vine, to give us pleasure, and these things could not be transported on land without the invention of the mechanism of carts or wagons, nor on the sea without that of ships. 6. The discovery of the method of testing weights by steelyards and balances saves us from fraud by introducing honest practices into life. There are also innumerable ways of employing machinery about which it seems unnecessary to speak, since they are at hand every day, such as mills, blacksmiths' bellows, carriages, gigs, turning lathes, and other things which are habitually used as general conveniences. Hence, we shall begin by explaining those that rarely come to hand, so that they may be understood. End of Book 10, Chapter 1. Book 10, Chapter 2 of 10 books on architecture. This LibriVox recording is in public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitrúvio. Translated by Morris Hickey Morgan. Chapter 2. Hoisting machines. 1. First we shall treat of those machines which are of necessity made ready when temples and public buildings are to be constructed. 2 timbers are provided strong enough for the weight of the load. They are fastened together at the upper end by a bolt, then spread apart at the bottom, and so set up, being kept upright by ropes attached at the upper ends and fixed at intervals all round. At the top is fastened a block, which some call a rechamus. In the block 2 sheaves are enclosed, turning on axles. The traction rope is carried over the sheave at the top, then let fall and passed round a sheave in a block below. Then it is brought back to a sheave at the bottom of the upper block, and so it goes down to the lower block, where it is fastened through a hole in that block. The other end of the rope is brought back and down between the legs of the machine. 2. Socket pieces are nailed to the hinder faces of the squared timbers at the point where they are spread apart, and the ends of the windlass are inserted into them so that the axles may turn freely. Close to each end of the windlass are 2 holes, so adjusted that handspikes can be fitted into them. To the bottom of the lower blocks are fastened shears made of iron, whose prongs are brought to bear upon the stones which have holes bored in them. When one end of the rope is fastened to the windlass, and the latter is turned round by working the handspikes, the rope winds round the windlass, gets taut, and thus it raises the load to the proper height and to its place in the work. 3. This kind of machinery, revolving with 3 sheaves, is called a trispast. When there are 2 sheaves turning in the block beneath and 3 in the upper, the machine is termed a pentaspast. But if we have to furnish machines for heavier loads, we must use timbers of greater length and thickness, providing them with correspondingly large bolts of the top, and windlasses turning at the bottom. When these are ready, let 4 stays be attached and left lying slack in front. Let the backstays be carried over the shoulders of the machine to some distance, and, if there is nothing to which they can be fastened, sloping piles should be driven, the ground rammed down all round to fix them firmly, and the ropes made fast to them. 4. A block should then be attached by a stout cord to the top of the machine, and from that machine a rope should be carried to a pile, and to a block tied to the pile. Let the rope be put in round the sheave of this block, and brought back to the block that is fastened at the top of the machine. Round its sheave the rope should be passed, and then should go down from the top and back to the windlass, which is at the bottom of the machine, and there be fastened. The windlass is now to be turned by means of the handspikes, and it will raise the machine of itself without danger. Thus a machine of the larger kind will be set in position with its ropes in their places about it, and its stays attached to the piles. Its blocks and traction ropes are arranged as described above. 5. But if the loads of the material for the work are still more colossal in size and weight, we shall not entrust them to a windlass, but set in an axle tree held by sockets as the windlass was, and carrying on its centre a large drum, which some term a wheel, but the Greeks call it amphisis or peritekion. 6. And the blocks of such machines are not arranged in the same but in a different manner, for the rows of sheaves in them are doubled, both at the bottom and at the top. The traction rope is passed through a hole in the lower block, in such a way that the 2 ends of the rope are of equal length when it is stretched out, and both portions are held there at the lower block by a cord which is passed round them and lashed so that they cannot come out either to the right or the left. Then the ends of the rope are brought up into the block at the top from the outside and passed down over its lower sheaves, and so return to the bottom, and are passed from the inside to the sheaves in the lowest block, and then are brought up on the right and left and returned to the top and round the highest set of sheaves. 7. Passing over these from the outside, they are then carried to the right and left of the drum on the axle tree, and are tied there as to stay fast. Then another rope is wound round the drum and are carried to a capstan, and when that is turned, it turns the drum and the axle tree. The ropes get taut as they wind round regularly, and thus they raise the load smoothly and with no danger. But if a large drum is placed either in the middle or at one side without any capstan, men can tread in it and accomplish the work more expeditiously. 8. There is also another kind of machine, ingenious enough and easy to use with speed, but only experts can work with it. It consists of a single timber, which is set up and held in place by stays on 4 sides. 2 cheeks are nailed on below the stays, a block is fastened by ropes above the cheeks, and a straight piece of wood above 2 feet long, 6 digits wide, and 4 digits thick, is put under the block. The blocks used have each 3 rows of sheaves side by side. Hence 3 traction ropes are fastened at the top of the machine. Then they are brought to the block at the bottom and passed from inside round the sheaves that are nearest the top of it. Then they are brought back to the upper block and passed inwards from outside round the sheaves nearest the bottom. 9. On coming down to the block at the bottom, they are carried round its second row of sheaves from the inside to the outside and brought back to the second row at the top, passing round it and returning to the bottom. Then from the bottom they are carried to the summit, where they pass round the highest row of sheaves and then return to the bottom of the machine. At the foot of the machine a third block is attached. The Greeks call it epagon, but our people artemon. This block, fastened at the foot of the machine, has 3 sheaves in it, round which the ropes are passed and then delivered to men to pull. Thus 3 rows of men, pulling without a capstan, can quickly raise the load to the top. 10. This kind of machine is called a polyspast, because of the many revolving sheaves to which its dexterity and dispatch are due. There is also this advantage in the erection of only a single timber, that by previously inclining it to the right or left as much as one wishes, the load can be set down at one side. All these kinds of machinery described above are in their principles suited not only to the purposes mentioned, but also to the loading and unloading of ships, some kinds being set upright and others placed horizontally on revolving platforms. On the same principle, ships can be hauled ashore by means of arrangements of ropes and blocks used on the ground without setting up timbers. 11. It may also not be out of place to explain the ingenious procedure of Chersiphron. Desiring to convey the shafts of the temple of Diana at Ephesus from the stone quarries, and not trusting to carts, lest their wheels should be engulfed on account of the great weights of the load and the softness of the roads in the plain, he tried the following plan. Using 4-inch timbers, he joined 2 of them, each as long as the shaft, with 2 crosspieces set between them, dovetailing all together, and then leaded iron gudgeons shaped like dovetails into the ends of the shafts, as dowels are leaded, and in the woodwork he fixed rings to contain the pivots and fastened wooden cheeks to the ends. The pivots, being enclosed in the rings, turned freely, so, when yokes of oxen began to draw the 4-inch frame, they made the shaft revolve constantly, turning it by means of the pivots and rings. 12. When they had thus transported all the shafts, and it became necessary to transport the architraves, Chersiphron's son Metagenes extended the same principle from the transportation of the shafts to the bringing down of the architraves. He made wheels, each about 12 feet in diameter, and enclosed the ends of the architraves in the wheels. In the ends he fixed pivots and rings in the same way. So when the 4-inch frames were drawn by oxen, the wheels turned on the pivots enclosed in the rings, and the architraves, which were enclosed like axles in the wheels, soon reached the building, in the same way as the shafts. The rollers used for smoothing the walks in palaestrae will serve as an example of this method, but it could not have been employed unless the distance had been short, for it is not more than 8 miles from the stone quarries to the temple, and there is no hill, but an uninterrupted plain. 13. In our own times, however, when the pedestal of the colossal Apollo in his temple had cracked with age, they were afraid that the statue would fall and be broken, and so they contracted for the cutting of a pedestal from the same quarries. The contract was taken by one Paconius. This pedestal was 12 feet long, 8 feet wide, and 6 feet high. Paconius, with confident pride, did not transport it by the method of Metagenes, but determined to make a machine of a different sort, though on the same principle. 14. He made wheels of about 15 feet in diameter, and in these wheels he enclosed the ends of the stone. Then he fastened 2-inch crossbars from wheel to wheel round the stone, encompassing it, so that there was an interval of not more than 1 foot between bar and bar. Then he coiled a rope round the bars, yoked up his oxen, and began to draw on the rope. Consequently, as it uncoiled, it did indeed cause the wheels to turn, but it could not draw them in a line straight along the road, but kept swerving out to one side. Hence it was necessary to draw the machine back again. Thus, by this drawing to and fro, Paconius got into such financial embarrassment that he became insolvent. 15. I will digress a bit and explain how these stone quarries were discovered. Pixodorus was a shepherd who lived in that vicinity. When the people of Ephesus were planning to build the temple of Diana in marble, and debating whether to get the marble from Paros, Proconnesus, Heraclea, or Thasus, Pixodorus drove out his sheep and was feeding his flock in that very spot. Then 2 rams ran at each other, and, each passing the other, one of them, after his charge, struck his horns against a rock, from which a fragment of extremely white colour was dislodged. So it is said that Pixodorus left his sheep in the mountains and ran down to Ephesus carrying the fragment, since that very thing was the question of the moment. Therefore they immediately decreed honours to him and changed his name, so that instead of Pixodorus he should be called Evangelus. And to this day the chief magistrate goes out to that very spot every month and offers sacrifice to him, and if he does not, he is punished. End of Book 10, Chapter 2. Book 10, Chapter 3 to 6 of 10 books on architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitrúvio, translated by Morris Hickey Morgan. Chapter 3. The elements of motion. 1. I have briefly set forth what I thought necessary about the principles of hoisting machines. In them 2 different things, unlike each other, work together as elements of their motion and power to produce these effects. One of them is the right line, which the Greeks term eptheia. The other is the circle, which the Greeks call kyklote. But in point of fact, neither rectilinear without circular motion, nor revolutions without rectilinear motion, can accomplish the raising of loads. I will explain this so that it may be understood. 2. As centers, axles are inserted into the sheaves, and these are fastened in the blocks, and rope carried over the sheaves, drawn straight down and fastened to a windlass, causes the load to move upward from its place as the handspikes are turned. The pivots of this windlass, lying as centers in right lines in its socket pieces, and the handspikes inserted in its holes, make the load rise when the ends of the windlass revolve in a circle like a lathe. Just so, when an iron lever is applied to a weight which a great many hands cannot move, with the fulcrum, which the Greeks called hupomokleon, lying as a center in a right line under the lever, and with the tongue of the lever placed under the weight, one man's strength, bearing down upon the head of it, heaves up the weight. 3. For, as the shorter forepart of the lever goes under the weight from the fulcrum that forms the center, the head of it, which is farther away from that center, on being depressed is made to describe a circular movement, and thus by pressure brings to an equilibrium the weight of a great very load by means of a few hands. Again, if the tongue of an iron lever is placed under a weight, and its head is not pushed down, but, on the contrary, is heaved up, the tongue supported on the surface of the ground will treat that as the weight, and the edge of the weight itself as the fulcrum. Thus, not so easily as by pushing down, but by motion in the opposite direction, the weight of the load will nevertheless be raised. If, therefore, the tongue of a lever lying on a fulcrum goes too far under the weight, and its head exerts its pressure too near the center, it will not be able to elevate the weight, nor can it do so unless, as described above, the length of the lever is brought to equilibrium by the depression of its head. 4. This may be seen from the balances that we call steel yards. When the handle is set as a center close to the end from which the scale hangs, and the counterpoise is moved along towards the other arm of the beam, shifting from point to point as it goes farther or even reaches the extremity, a small and inferior weight becomes equal to a very heavy object that is being weighed, on account of the equilibrium that is due to the leveling of the beam. Thus, as it withdraws from the center, a small and comparatively light counterpoise, slowly turning the scale, makes a greater amount of weight rise gently upwards from below. 5. So too, the pilot of the biggest merchantman, grasping the steering oar by its handle, which the Greeks call oix, and with one hand bringing it to the turning point according to the rules of his art, by pressure about a center, can turn the ship, although she may be laden with a very large or even enormous burden of merchandise and provisions. And when her sails are set only half-way up the mast, a ship cannot run quickly, but when the yard is hoisted to the top, she makes much quicker progress, because then the sails get the wind, not when they are too close to the heel of the mast, which represent the center, but when they have moved farther away from it to the top. 6. As a lever thrust under a weight is harder to manage and does not put forth its strength if the pressure is exerted at the center, but easily raises the weight when the extreme end of it is pushed down, so sails that are only half-way up have less effect, but when they get farther away from the center and are hoisted to the very top of the mast, the pressure at the top forces the ship to make greater progress, though the wind is no stronger but just the same. Again, take the case of oars, which are fastened to the tholes by loops. When they are pushed forward and drawn back by the hand, if the ends of the blades are at some distance from the center, the oars foam with the waves of the sea and drive the ship forward in a straight line with a mighty impulse, while her prow cuts through the rare water. 7. And when the heaviest burdens are carried on poles by 4 or 6 porters at a time, they find the centers of balance at the very middle of the poles, so that, by distributing the dead weight of the burden according to a definitely proportioned division, each laborer may have an equal share to carry on his neck. For the poles, from which the straps for the burden of the 4 porters hang, are marked off at their centers by nails to prevent the straps from slipping to one side. If they shift beyond the mark at the center, they weigh heavily upon the place to which they have come nearer, like the weight of a steel yard when it moves from the point of equilibrium towards the ends of the weighing apparatus. 8. In the same way, oxen have an equal draught when their yoke is adjusted at its middle by the yoke strap to the pole. But when their strength is not the same, and the stronger outdoes the other, the strap is shifted so as to make one side of the yoke longer, which helps the weaker ox. Thus, in the case of both poles and yokes, when the straps are not fastened at the middle, but at one side, the farther the strap moves from the middle, the shorter it makes one side, and the longer the other. So, if both ends are carried round in circles, using as a center the point to which the strap has been brought, the longer end will describe a larger and the shorter end a smaller circle. 9. Just as smaller wheels move harder and with greater difficulty than larger ones, so, in the case of poles and yokes, the parts where the intervals from the center to end is less, bear down hard upon the neck, but where the distance from the same center is greater, they ease the burden both for draught and carriage. As in all these cases motion is obtained by means of right lines at the center and by circles, so also farm wagons, travelling carriages, drums, mills, screws, scorpiones, ballistae, press beams, and all other machines produce the results intended on the same principles, by turning about a rectilinear axis and by the revolution of a circle. Chapter 4. Engines for raising water. 1. I shall now explain the making of the different kinds of engines which have been invented for raising water, and will first speak of the tympanum. Although it does not lift the water high, it raises a great quantity very quickly. An axle is fashioned on a lathe or with compasses, its ends are shod with iron hoops, and it carries round its middle a tympanum made of boards joined together. It rests on posts which have pieces of iron on them under the ends of the axle. In the interior of this tympanum there are 8 crosspieces set at intervals, extending from the axle to the circumference of the tympanum, and dividing the space in the tympanum into equal compartments. 2. Planks are nailed round the face of it, leaving 6-inch apertures to admit the water. At one side of it there are also holes, like those of a dovecot, next to the axle, one for each compartment. After being smeared with pitch like a ship, the thing is turned by the thread of men, and raising the water by means of the apertures in the face of the tympanum, delivers it through the holes next to the axle into a wooden trough set underneath, with a conduit joined to it. Thus a large quantity of water is furnished for irrigation in gardens or for supplying the needs of salt works. 3. But when it has to be raised higher, the same principle will be modified as follows. A wheel on an axle is to be made, large enough to reach the necessary height. All round the circumference of the wheel there will be cubical boxes, made tight with pitch and wax, so when the wheel is turned by treading, the boxes, carried up full and again returning to the bottom, will of themselves discharge into the reservoir what they have carried up. 4. But if it has to be supplied to a place still more high, a double iron chain, which will reach the surface when let down, is passed round the axle of the same wheel, with bronze buckets attached to it, each holding about 6 pints. The turning of the wheel, winding the chain round the axle, will carry the buckets to the top, and as they pass above the axle they must tip over and deliver it into the reservoir what they have carried up. Chapter 5. Water wheels and water mills. 1. Wheels on the principles that have been described above are also constructed in rivers. Round their faces floatboards are fixed, which, on being struck by the current of the river, make the wheel turn as they move, and thus, by raising the water in the boxes and bringing it to the top, they accomplish the necessary work through which being turned by the mere impulse of the river, without any treading on the part of workmen. 2. Water mills are turned on the same principle. Everything is the same in them, except that a drum with teeth is fixed into one end of the axle. It is set vertically on its edge, and turns in the same plane with the wheel. Next to this larger drum there is a smaller one, also with teeth, but set horizontally, and this is attached to the millstone. Thus the teeth of the drum, which is fixed to the axle, make the teeth of the horizontal drum move and cause the mill to turn. A hopper hanging over this contrivance supplies the mill with corn, and meal is produced by the same revolution. Chapter 6. The water screw. 1. There is also the method of the screw, which raises a great quantity of water, but does not carry it as high as does the wheel. The method of constructing it is as follows. A beam is selected, the thickness of which in digits is equivalent to its length in feet. This is made perfectly round. The ends are to be divided off on their circumference with the compass into 8 parts, by quadrants and octants, and let the lines be so placed that if the beam is laid in a horizontal position, the lines on the two ends may perfectly correspond with each other, and intervals of the size of 1/8 part of the circumference of the beam may be laid off on the length of it. Then, placing the beam in a horizontal position, let perfectly straight lines be drawn from one end to the other, so the intervals will be equal in the directions both of the periphery and of the length. Where the lines are drawn along the length, the cutting circles will make intersections, and definite points at the intersections. 2. When these lines have been correctly drawn, a slender width of the willow, or a straight piece cut from the agnus castus tree, is taken, smeared with liquid pitch, and fastened at the first point of intersection. Then it is carried across obliquely to the succeeding intersections of longitudinal lines and circles, and as it advances, passing each of the points in due order and winding round, it is fastened at each intersection. And so, withdrawing from the first to the 8th point, it reaches and is fastened to the line to which its first part was fastened. Thus it makes as much progress in its longitudinal advance to the 8th point as in its oblique advance over 8 points. In the same manner, widths for the 8 divisions of the diameter, fastened obliquely at the intersections on the entire longitudinal and peripheral surface, make spiral channels which naturally look just like those of a snail shell. 3. Other widths are fastened on the line of the first, and on these still others, all smeared with liquid pitch and built up until the total diameter is equal to 1/8 of the length. These are covered and surrounded with boards fastened on to protect the spiral. Then these boards are soaked with pitch and bound together with strips of iron, so that they may not be separated by the pressure of the water. The ends of the shaft are covered with iron. To the right and left of the screw are beams, with cross pieces fastening them together at both ends. In these cross pieces are holes sheathed with iron, and into them pivots are introduced, and thus the screw is turned by the treading of men. 4. It is to be set up at an inclination corresponding to that which is produced in drawing the Pythagorean right-angled triangle. That is, let its length be divided into 5 parts, let 3 of them denote the height of the head of the screw, thus the distance from the base of the perpendicular to the nozzle of the screw at the bottom will be equal to 4 of those parts. A figure showing how this ought to be has been drawn at the end of the book, right on the back. I have now described as clearly as I could, to make them better known, the principles on which wooden engines for raising water are constructed, and how they get their motion so that they may be of unlimited usefulness through their revolutions. End of Book 10, Chapter 6. Book 10, Chapter 7 to 10 of 10 Books on Architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 Books on Architecture by Vitrúvio, translated by Morris Hickey Morgan. Chapter 7. The Pump of Ctesibius. 1. Next I must tell about the machine of Ctesibius, which raises water to a height. It is made of bronze, and has at the bottom a pair of cylinders set a little way apart, and there is a pipe connected with each, the two running up like the prongs of a fork, side by side, to a vessel which is between the cylinders. In this vessel are valves, accurately fitting over the upper vents of the pipes, which stop up the vent holes and keep what has been forced by pressure into the vessel from going down again. 2. Over the vessel a cowl is adjusted, like an inverted funnel, and fastened to the vessel by means of a wedge thrust through a staple to prevent it from being lifted off by the pressure of the water that is forced in. On top of this a pipe is jointed, called the trumpet, which stands up vertically. Valves are inserted in the cylinders, beneath the lower vents of the pipes, and over the openings which are in the bottoms of the cylinders. 3. Pistons, smoothly turned, rubbed with the oil, and inserted from above into the cylinders, work with the rods and levers upon the air and water in the cylinders, and, as the valves stop up the openings, force and drive the water by repeated pressure and expansion through the vents of the pipes into the vessel, from which the cowl receives the inflated currents, and sends them through the pipe at the top, and so water can be supplied for a fountain from a reservoir at a lower level. 4. This, however, is not the only apparatus which Ctesibius is said to have thought out, but many more of various kinds are shown by him to produce effects borrowed from nature by means of water pressure and compression of the air, as, for example, blackbirds singing by means of waterworks, and angobatai and figures that drink and move, and other things that are found to be pleasing to the eye and the ear. 5. Of these I have selected what I considered most useful and necessary, and I have thought it best to speak in the preceding book about timepieces, and in this about the methods of raising water. The rest, which are not subservient to our needs but to pleasure and amusement, may be found in the commentaries of Ctesibius himself by any who are interested in such refinements. Chapter 8. The Water Organ. 1. With regard to water organs, however, I shall not fail with all possible brevity and precision to touch upon their principles, and to give a sufficient description of them. A wooden base is constructed, and on it is set an altar-shaped box made of bronze. Uprights, fastened together like ladders, are set up on the base to the right and to the left of the altar. They hold the bronze pump cylinders, the movable bottoms at which, carefully turned on a lathe, have iron elbows fastened to their centers and jointed to levers, and are wrapped in fleeces of wool. In the tops of the cylinders are openings, each about 3 digits in diameter. Close to these openings are bronze dolphins, mounted on joints and holding chains in their mouths, from which hang cymbal-shaped valves let down under the openings in the cylinders. 2. Inside the altar, which holds the water, is a regulator shaped like an inverted funnel, under which there are cubes, each about 3 digits high, keeping a free space below between the lips of the regulator and the bottom of the altar. Tightly fixed on the neck of the regulator is the wind chest, which supports the principal part of the contrivance, called in Greek the kanon musikos. Running longitudinally, there are 4 channels in it if it is a tetrachord, 6 if it is a hexachord, 8 if it is an octachord. 3. Each of the channels has a cock in it, furnished with an iron handle. These handles, when turned, open vent holes from the windchest into the channels. From the channels to the cannon there are vertical openings corresponding to vent holes in a board above, which board is termed pinax in Greek. Between this board and the cannon are inserted sliders, pierced with holes to correspond and rubbed with oil so that they can easily be moved and slid back into place again. They close the above-mentioned openings and are called the plinths. Their going and coming now closes and now opens the holes. 4. These sliders have iron jacks fixed to them and connected with the keys, and the keys, when touched, make the sliders move regularly. To the upper surface of the openings in the board, where the wind finds egress from the channels, rings are soldered, and into them the reeds of all the organ pipes are inserted. From the cylinders there are connecting pipes attached to the neck of the regulator and directed towards the vent holes in the windchest. In the pipes are valves, turned on a lathe, and set where the pipes are connected with the cylinders. When the windchest has received the air, these valves will stop up the openings and prevent the wind from coming back again. 5. So, when the levers are raised, the elbows draw down the bottoms of the cylinders as far as they can go, and the dolphins, which are mounted on joints, let the cymbals fall into the cylinders, thus filling the interiors with air. Then the elbows, raising the bottoms within the cylinders by repeated and violent blows, and stopping the openings above by means of the cymbals, compress the air which is enclosed in the cylinders, and force it into the pipes, through which it runs into the regulator and through its neck into the windchest. With a stronger motion of the levers, the air is still more compressed, streams through the apertures of the cocks, and fills the channels with wind. 6. So when the keys, touched by the hand, drive the sliders forward and draw them back regularly, alternately stopping and opening the holes, they produce resonant sounds in a great variety of melodies conforming to the laws of music. With my best efforts I have striven to set forth an obscure subject clearly in writing, but the theory of it is not easy, nor clearly understood by all, save only those who have had some practice in things of this kind. If anybody has failed to understand it, he will certainly find, when he comes to know the thing itself, that it is carefully and exquisitely contrived in all respects. Chapter 9. The hodometer. 1. The drift of our treatise now turns to a useful invention of the greatest ingenuity, transmitted by our predecessors, which enables us, while sitting in a carriage on the road or sailing by sea, to know how many miles of a journey we have accomplished. This will be possible as follows. Let the wheels of the carriage be each 4 feet in diameter, so that if a wheel has a mark made upon it and begins to move forward from that mark in making its revolution on the surface of the road, it will have covered the definite distance of 12.5 feet on reaching the mark at which it began to revolve. 2. Having provided such wheels, let a drum with a single tooth, projecting beyond the face of its circumference, be firmly fastened to the inner side of the hub of the wheel. Then, above this, let a case be firmly fastened to the body of the carriage, containing a revolving drum set on edge and mounted on an axle. On the face of the drum there are 400 teeth, placed at equal intervals and engaging the tooth of the drum below. The upper drum has, moreover, one tooth fixed to its side and standing out farther than the other teeth. 3. Then, above, let there be a horizontal drum, similarly toothed and contained in another case, with its teeth engaging the tooth fixed to the side of the second drum, and let as many holes be made in this third drum as will correspond to the number of miles, more or less, it does not matter, that a carriage can go in a day's journey. Let a small round stone be placed in every one of these holes, and in the receptacle or case containing that drum let one hole be made, with a small pipe attached, through which, when they reach that point, the stone placed in the drum may fall one by one into a bronze vessel set underneath in the body of the carriage. 4. Thus, as the wheel in going forward carries with it the lowest drum, and as the tooth of this at every revolution strikes against the teeth of the upper drum and makes it move along, the result will be that the upper drum is carried round once for every 400 revolutions of the lowest, and that the tooth fixed to this side pushes forward one tooth of the horizontal drum. Since, therefore, with 400 revolutions of the lowest drum the upper will revolve once, the progress made will be a distance of 5,000 feet or 1 mile. Hence, every stone making a ringing sound as it falls will give warning that we have gone 1 mile. The number of stones gathered from beneath and counted will show the number of miles in the day's journey. 5. On board ship, also the same principle may be employed with a few changes. An axle is passed through the sides of the ship, with its ends projecting, and wheels are mounted on them, 4 feet in diameter, with projecting floatboards fastened round their faces and striking the water. The middle of the axle in the middle of the ship carries a drum with one tooth projecting beyond its circumference. Here a case is placed containing a drum with 400 feet at regular intervals, engaging the tooth of the drum that is mounted on the axle, and having also one other tooth fixed to its side and projecting beyond its circumference. 6. Above, in another case fastened to the former, is a horizontal drum toothed in the same way, and with its teeth, engaging the tooth fixed to the side of the drum that is set on edge, so that one of the teeth of the horizontal drum is struck at each revolution of that tooth, and the horizontal drum is thus made to revolve in a circle. Let holes be made in the horizontal drum, in which holes small round stones are to be placed. In the receptacle or case containing that drum, let one hole be opened with a small pipe attached, through which a stone, as soon as the obstruction is removed, falls with a ringing sound into a bronze vessel. 7. So, when the ship is making headway, whether under oars or under a gale of wind, the floatboards on the wheels will strike against the water and be driven violently back, thus turning the wheels, and they, revolving, will move the axle, and the axle the drum, the tooth of which, as it goes round, strikes one of the teeth of the second drum at each revolution, and makes it turn a little. So, when the floatboards have caused the wheels to revolve 400 times, this drum, having turned round once, will strike a tooth of the horizontal drum with the tooth that is fixed to its side. Hence, every time the turning of the horizontal drum brings a stone to a hole, it will let the stone out through the pipe. Thus, by the sound and the number, the length of the voyage will be shown in miles. I have described how to make things that may be provided for use and amusement in times that are peaceful and without fear. Chapter 10. Catapults or scorpiones. 1. I shall next explain the symmetrical principles on which scorpiones and ballistae may be constructed, inventions devised for defense against danger and in the interest of self-preservation. The proportions of these engines are all computed from the given length of the arrow which the engine is intended to throw, and the size of the holes in the capitals, through which the twisted sinews that hold the arms are stretched, is 1/9 of that length. 2. The height and breadth of the capital itself must then conform to the size of the holes. The boards at the top and bottom of the capital, which are called peritreti, should be in thickness equal to one hole, and in breadth to 1 3/4, except at their extremities, where they equal 1 1/2. The side posts on the right and left should be 4 holes high, excluding the tenons, and 5/12 of a hole thick, the tenons half a hole. The distance from a side post to the hole is 1/4 of a hole, and it is also 1/4 of a hole from the hole to the post in the middle. The breadth of the post in the middle is equal to 1 hole and 1/8, the thickness to 1 hole. 3. The opening in the middle post, where the arrow is laid, is equal to 1/4 of the hole. The 4 surrounding corners should have iron plates nailed to their sides and faces, or should be studded with bronze pins and nails. The pipe, called syrinx in Greek, has a length of 19 holes. The strips, which some term cheeks, nailed at the right and left of the pipe, have a length of 19 holes and a height and thickness of 1 hole. 2 other strips enclosing the windlass are nailed on to these, 3 holes long and half a hole in breadth. The cheek nailed onto them, named the bench, or by some the box, and made fast by means of the dovetail tenons, is 1 hole thick and 7/12 of a hole in height. The length of the windlass is equal to holes, the thickness of the windlass to 3/4 of a hole. 4. The latch is 7/12 of a hole in length and 1/4 in thickness, so also its socket piece. The trigger or handle is 3 holes in length and 3/4 of a hole in breadth and thickness. The trough in the pipe is 16 holes in length, 1/4 of a hole in thickness, and 3/4 in height. The base of the standard on the ground is equal to 8 holes. The breadth of the standard where it is fastened into the plinth is 3/4 of a hole, its thickness 2/3 of a hole, The height of the standard up to the tenon is 12 holes, its breadth 3/4 of a hole, and its thickness 2/3. It has 3 struts, each 9 holes in length, half a hole in breadth, and 5/12 in thickness. The tenon is 1 hole in length, and the head of the standard 1 hole and a half in length. 5. The antefix has the breadth of a hole and 1/8, and the thickness of 1 hole. The smaller support, which is behind, termed in Greek antibasis, is 8 holes long, 3/4 of a hole broad, and 2/3 thick. Its prop is 12 holes long, and has the same breadth and thickness as the smaller support just mentioned. Above the smaller support is its socket piece, or what is called the cushion, 2½ holes long, 1½ high, and 3/4 of a hole broad. The windlass cup is 2 7/12 holes long, 2/3 of a hole thick, and 3/4 broad. The cross pieces with their tenons have the length of holes, the breadth of 3/4, and the thickness of 2/3 of a hole. The length of an arm is 7 holes, its thickness at its base 2/3 of a hole, and at its end 1/2 a hole. Its curvature is equal to 2/3 of a hole. 6. These engines are constructed according to these proportions or with additions or diminutions. For, if the height of the capitals is greater than the width, when they are called high-tensioned, something should be taken from the arms, so that the more the tension is weakened by height of the capitals, the more the strength of the blow is increased by shortness of the arms. But if the capital is less high, when the term low-tensioned is used, the arms, on account of the strength, should be made a little longer, so that they may be drawn easily. Just as it takes 4 men to raise a load with a lever 5 feet long, and only 2 men to lift the same load with a 10-foot lever, so the longer the arms, the easier they are to draw, and the shorter, the harder. I have now spoken of the principles applicable to the parts and proportions of catapults. End of Book 10, Chapter 10. Book 10, chapters 11 to 13 of 10 books on architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitrúvio, translated by Morris Hickey Morgan. Chapter 11. Ballistae. 1. Ballistae are constructed on varying principles to produce an identical result. Some are worked by hand spikes and windlasses, some by blocks and pulleys, others by capstans, others again by means of drums. No ballista, however, is made without regard to the given amount of weight of the stone which the engine is intended to throw. Hence their principle is not easy for everybody, but only for those who have knowledge of the geometrical principles employed in calculation and in multiplication. 2. For the holes made in the capitals, through the openings of which are stretched the strings made of twisted hair, generally women's, or of sinew, are proportionate to the amount of weight in the stone which the ballista is intended to throw, and to the principle of mass. As in catapults, the principle is that of the length of the arrow. Therefore, in order that those who do not understand geometry may be prepared beforehand, so as not to be delayed by having to think the matter out at a moment of peril in war, I will set forth what I myself know by experience can be depended upon, and what I have in part gathered from the rules of my teachers. And wherever Greek weights bear a relation to the measures, I shall reduce and explain them so that they will express the same corresponding relation in our weights. 3. A ballista intended to throw a 2-pound stone will have a hole of 5 digits in its capital, 4 pounds 6 digits, and 6 pounds 7 digits, 10 pounds 8 digits, 20 pounds 10 digits, 40 pounds 12½ digits, 60 pounds 13½ digits, 80 pounds 15¾ digits, 100 pounds 1 foot and 1½ digits. 120 pounds 1 foot and 2 digits, 140 pounds 1 foot and 3 digits, 160 pounds 1 foot and a quarter, 180 pounds 1 foot and 5 digits, 200 pounds 1 foot and 6 digits, 240 pounds 1 foot and 7 digits, 280 pounds 1 foot and a half, 320 pounds 1 foot and 9 digits, 360 pounds 1 foot and 10 digits. 4. Having determined the size of the hole, design the scutula, termed in Greek peritretos, holes in length and 2 1/6 in breadth. Bisect it by a line drawn diagonally from the angles, and after this bisecting, bring together the outlines of the figure so that it may present a rhomboidal design, reducing it by 1/6 of its length and 1/4 of its breadth at the obtuse angles. In the part composed by the curvatures into which the points of the angles run out, let the holes be situated, and let the breadth be reduced by 1/6. Moreover, let the hole be longer than it is broad by the thickness of the bolt. After designing the scutula, let its outline be worked down to give it a gentle curvature. 5. It should be given the thickness of 7/12 of a hole. The boxes are 2 holes in height, 1 3/4 in breadth, 2/3 of a hole in thickness except the part that is inserted in the hole, and at the top 1/3 of a hole in breadth. The side posts are 5 holes and 2/3 in length, their curvature half a hole, and their thickness 37/48 of a hole. In the middle their breadth is increased as much as it was near the hole in the design by the breadth and thickness of hole, the height by 1/4 of a hole. 6. The inner strip on the table has a length of 8 holes, a breadth and thickness of half a hole. Its tenons are 1 hole and 1/6 long, and 1/4 of a hole in thickness. The curvature of this strip is 3/4 of a hole. The outer strip has the same breadth and thickness as the inner, but the length is given by the obtuse angle of the design and the breadth of the side post at its curvature. The upper strips are to be equal to the lower, the crosspieces of the table 1/2 of a hole. 7. The shafts of the ladder are 13 holes in length, 1 hole in thickness, the space between them is 1 hole and 1/4 in breadth, and 1 1/8 in depth. Let the entire length of the ladder on its upper surface, which is the one adjoining the arms and fastened to the table, be divided into 5 parts. Of these let 2 parts be given to the member which the Greeks call cheloinion, its breadth being 1 1/6, its thickness 1/4, and its length 11 holes and 1/2. The claw projects half a hole and the winging 3/16 of a hole. What is at the axis which is termed the face? The cross pieces of 3 holes? 8. The breadth of the inner slips is 1/4 of a hole, their thickness 1/6. The cover joint or lid of the chelonium is dovetailed into the shafts of the ladder, and is 3/16 of a hole in breadth and 1/12 in thickness. The thickness of the square piece on the ladder is 3/16 of a hole. The diameter of the round axle will be equal to that of the claw, but at the pivots 7/16 of a hole. The stays are holes in length, 1/4 of a hole in breadth at the bottom, and 1/6 in thickness at the top. The base, termed escara, has the length of holes and the anti-base of 4 holes. Each is 1 hole in thickness and breadth. A supporter is jointed on halfway up, 1 1/2 holes in breadth and thickness. Its height bears no relation to the hole, but will be such as to be serviceable. The length of an arm is 6 holes, its thickness at the base 2/3 of a hole, and at the end 1/2 a hole. I have now given those symmetrical proportions of ballistae and catapults which I thought most useful, but I shall not omit, so far as I can express it in writing, the method of stretching and turning the strings of twisted sinew or hair. Chapter 12. The stringing and tuning of catapults. 1. Beams of very generous length are selected, and upon them are nailed socket pieces in which windlasses are inserted. Midway along their length the beams are incised and cut away to form framings, and in these cuttings the capitals of the catapults are inserted, and prevented by wedges from moving when the stretching is going on. Then the bronze boxes are inserted into the capitals, and the little iron bolts, which the Greeks call epizygides, are put in their places in the boxes. 2. Next the loops of the strings are put through the holes in the capitals and passed through to the other side. Next they are put upon the windlasses and wound round them in order that the strings, stretched out taut on them by means of the handspikes, on being struck by the hand, may respond with the same sound on both sides. Then they are wedged tightly into the holes so that they cannot slacken. So, in the same manner, they are passed through to the other side and stretched taut on the windlasses by means of the handspikes until they give the same sound. Thus, with the tight wedging, catapults are tuned to the proper pitch by musical sense of hearing. On these things I have said what I could. There is left for me, in the matter of sieges, to explain how generals can win victories and cities be defended by means of machinery. Chapter 13. Siege machines. 1. It is related that the battering ram for sieges was originally invented as follows. The Carthaginians pitched their camp for the siege of Cadiz. They captured an outwork and attempted to destroy it, but having no iron implements for its destruction, they took a beam, and, raising it with their hands, and driving the end of it repeatedly against the top of the wall, they threw down the top courses of stones, and thus, step by step, in regular order, they demolished the entire redoubt. 2. Afterwards, a carpenter from Tyre, bright by name and by nature, was led by this invention into setting up a mast from which he hung another crosswise like a steelyard, and so, by swinging it vigorously to and fro, he threw down the wall of Cadiz. Geras of Chalcedon was the first to make a wooden platform with wheels under it, under which he constructed a framework of uprights and crosspieces, and within it he hung the ram, and covered it with ox hide for the better protection of the men who were stationed in the machine to batter the wall. As the machine made but slow progress, he first gave it the name of the tortoise of the ram. 3. These were the first steps then taken towards that kind of machinery, but afterwards, when Philip, the son of Amyntas, was besieging Byzantium, it was developed in many varieties and made handier by Polyidus the Thessalian. His pupils were Diades and Carius, who served with Alexander. Diades shows in his writings that he invented movable towers, which he used also to take apart and carry round with the army, and likewise the borer and the scaling machine, by means of which one can cross over the wall on a level with the top of it, as well as the destroyer called the raven, or by others the crane. 4. He also employed the ram mounted on wheels, an account of which he left in his writings. As for the tower, he says that the smallest should be not less than 60 cubits in height and 17 in breadth, but diminishing to 1/5 less at the top, the uprights for the tower being 9 inches at the bottom and 1/2 foot at the top. Such a tower, he says, ought to be 10 stories high, with windows in it on all sides. 5. His larger tower, he adds, was 120 cubits high and 23½ cubits broad, diminishing like the other to 1/5 less. The uprights 1 foot at the bottom and 6 digits at the top. He made these large towers 20 stories high, each story having a gallery round it 3 cubits wide. He covered the towers with rawhide to protect them from any kind of missile. 6. The tortoise of the battering ram was constructed in the same way. It had, however, a base of 30 cubits square and a height, excluding the pediment, of 13 cubits. The height of the pediment from its bed to its top was 7 cubits. Issuing up and above the middle of the roof for not less than 2 cubits was a gable, and on this was reared a small tower 4 stories high, in which on the top floor scorpiones and catapults were set up, and on the lower floors a great quantity of water was stored to put out any fire that might be thrown on the tortoise. Inside of this was set the machinery of the ram, termed in Greek kriodike, in which was placed a roller turned on a lathe, and the ram, being set on top of this, produced its great effect when swung to and fro by means of ropes. It was protected, like the tower, with rawhide. 7. He explained the principles of the borer as follows: that the machine itself resembled the tortoise, but that in the middle it had a pipe lying between upright walls, like the pipe usually found in catapults and ballistae, 50 cubits in length and 1 cubit in height, in which a windlass was set transversely. On the right and left at the end of the pipe were 2 blocks, by means of which the iron-pointed beam which lay in the pipe was moved. There were numerous rollers enclosed in the pipe itself under the beam, which made its movements quicker and stronger. Numerous arches were erected along the pipe above the beam which was in it, to hold up the rawhide in which this machine was enveloped. 8. He thought it needless to write about the Raven because he saw that the machine was of no value. With regard to the scaling machine, termed in Greek epibathra, and the naval contrivances which, as he wrote, could be used in boarding ships, I have observed that he merely promised with some earnestness to explain their principles, but that he has not done so. I have set forth what was written by Diades on machines and their construction. I shall now set forth the methods which I have learned from my teachers and which I myself believe to be useful. End of Book 10, Chapter 13. Book 10, Chapter 14 to 16 of 10 books on architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitrúvio, translated by Morris Hickey Morgan. Chapter 14. The Tortoise. 1. A tortoise intended for the filling of ditches and thereby to make it possible to reach the wall is to be made as follows. Let a base, termed in Greek eskara, be constructed, with each of its sides 21 feet long and with 4 cross pieces. Let these be held together by 2 others, 2/3 of a foot thick and 1/2 a foot broad. Let the cross pieces be about 3 feet and a half apart, and beneath and in the spaces between them set the trees, termed in Greek hamaxopodes, in which the axles of the wheels turn in iron hoops. Let the trees be provided with pivots and also with holes through which the levers are passed to make them turn, so that the tortoise can move forward or back or towards its right or left side, or if necessary obliquely, all by the turning of the trees. 2. Let 2 beams be laid on the base, projecting for 6 feet on each side, round the projections of which let 2 other beams be nailed, projecting 7 feet beyond the former, and of the thickness and breadth prescribed in the case of the base. On this framework set up posts mortised into it, 9 feet high exclusive of their tenons, 1 foot and a quarter square and 1 foot and a half apart. Let the posts be tied together at the top by mortised beams. Over the beams let the rafters be set, tied one into another by means of tenons, and carried up 12 feet high. Over the rafters set the square beam by which the rafters are bound together. 3. Let the rafters themselves be held together by bridgings, and covered with boards, preferably of holm oak, or, this failing, of any other material which has the greatest strength, except pine or alder. For these woods are weak and easily catch fire. Over the boardings let there be placed wattles very closely woven of thin twigs as fresh as possible. Let the entire machine be covered with rawhide sewed together double and stuffed with seaweed or straw soaked in vinegar. In this way the blows of ballista and the force of fires will be repelled by them. Chapter 15. Hegetor's Tortoise. 1. There is also another kind of tortoise, which has all the other details as described above except rafters, but it has round it a parapet and battlements of boards, and eaves sloping downwards, and is covered with boards and hides firmly fastened in place. Above this let clay kneaded with hair be spread to such a thickness that fire cannot injure the machine. These machines can, if need be, have 8 wheels, should it be necessary to modify them with reference to the nature of the ground. Tortoises, however, which are intended for excavating, termed in Greek oryktides, have all the other details as described above, but their fronts are constructed like the angles of triangles, in order that when missiles are shot against them from a wall, they may receive the blows not squarely in front, but glancing from the sides, and those excavating within may be protected without danger. 2. It does not seem to be out of place to set forth the principles of which Hegetor of Byzantium constructed a tortoise. The length of its base was 63 feet, the breadth 42. The corner posts, 4 in number, which were set upon this framework, were made of 2 timbers each, and were 36 feet high, a foot and a quarter thick, and a foot and a half broad. The base had 8 wheels by means of which it is moved about. The height of these wheels was 6 3/4 feet, their thickness 3 feet. Thus constructed of 3 pieces of wood, united by alternate opposite dovetails and bowed together by cold-drawn iron plates, they revolved in the trees or amaxopodes. 3. Likewise on the plane of the crossbeams above the base were erected posts 18 feet high, 3/4 of a foot broad, 2/3 of a foot thick, and a foot and 3/4 apart. Above these, framed beams a foot broad and 3/4 of a foot thick held the whole structure together. Above this the rafters were raised with an elevation of 12 feet. A beam set above the rafters united their joinings. They also had bridgings fastened transversely, and a flooring laid on them protected the parts beneath. 4. It had, moreover, a middle flooring on girts, where scorpiones and catapults were placed. There were set up, also, 2 framed uprights 4 to 5 feet long, a foot and a half in thickness, and 3/4 of a foot in breadth, joined at the tops by amortised crossbeams, and by another halfway up mortised into the 2 shafts and tied in place by iron plates. Above this was set between the shafts and the crossbeams a block pierced on either side by sockets and firmly fastened in place with clamps. In this block were 2 axles turned on a lathe, and ropes fastened from them held the ram. 5. Over the head of these ropes which held the ram was placed a parapet fitted out like a small tower, so that, without danger, 2 soldiers, standing in safety, could look out and report what the enemy were attempting. The entire ram had a length of 180 feet, a breadth at the base of a foot and a quarter, and a thickness of a foot, tapering at the head to a breadth of a foot and a thickness of 3/4 of a foot. 6. This ram, moreover, had a beak of hard iron, such as ships of war usually have, and from the beak iron plates 4 in number, about 15 feet long, were fastened to the wood. From the head to the very heel of the beam were stretched cables, 3 in number and 8 digits thick, fastened just as in a ship from stem to stern continuously, and 3 cables were bound with cross girdles a foot and a quarter apart. Over these the whole ram was wrapped with rawhide. The ends of the ropes from which the ram hung were made of 4-fold chains of iron, and these chains were themselves wrapped in rawhide. 7. Likewise, the projecting end of the ram had a box framed and constructed of boards, in which was stretched a net made of rather large ropes, over the rough surfaces of which one easily reached the wall without the feet slipping, and this machine moved in 6 directions, forward and backward, also to the right or left, and likewise it was elevated by extending it upwards and depressed by inclining it downwards. The machine could be elevated to a height sufficient to throw down a wall of about 100 feet, and likewise in its thrust it covered a space from right to left of not less than 100 feet. 100 men controlled it, though it had a weight of 4,000 talents, which is 480,000 pounds. Chapter 16. Measures of defense. 1. With regard to scorpions, catapults, and ballistae, likewise with regard to tortoises and towers, I have set forth, as seemed to me especially appropriate, both by whom they were invented and in what manner they should be constructed. But I have not considered it as necessary to describe ladders, cranes, and other things, the principles of which are simpler, for the soldiers usually construct these by themselves. Nor can these very machines be useful in all places nor in the same way, since fortifications differ from each other, and so also the bravery of nations. For siege works against bold and venturesome men should be constructed on one plan, and on another against cautious men, and on still another against the cowardly. 2. And so, if one pays attention to these directions, and by selection adapts their various principles to a single structure, he will not be in need of further aids, but will be able without hesitation to design such machines as the circumstances or the situations demand. With regard to works of defense, it is not necessary to write, since the enemy do not construct their defenses in conformity with our books, but their contrivances are frequently foiled on the spur of the moment by some shrewd, hastily conceived plan without the aid of machines, as is said to have been the experience of the Rhodians. 3. For Diognetus was a Rhodian architect, to whom, as an honour, was granted out of the public treasury a fixed annual payment commensurate with the dignity of his art. At this time an architect from Aradus, Callias by name, coming to Rhodes, gave a public lecture and showed a model of a wall, over which he set a machine on a revolving crane, with which he seized an helepolis, as it approached the fortifications, and brought it inside the wall. The Rhodians, when they had seen this model, filled with admiration, took from Diognetus the yearly grant and transferred this honour to Callias. 4. Meanwhile, King Demetrius, who because of his stubborn courage was called Poliorcetes, making war on Rhodes, brought with him a famous Athenian architect named Epimachus. He constructed at enormous expense, with the utmost care and exertion, an helepolis 135 feet high and 60 feet broad. He strengthened it with hair and rawhide so that it could withstand the blow of a stone weighing 360 pounds shot from a ballista. The machine itself weighed 360,000 pounds. When Callias was asked by the Rhodians to construct a machine to resist this helepolis and to bring it within the wall as he had promised, he said that it was impossible. 5. For not all things are practicable on identical principles, but there are some things which, when enlarged in imitation of small models, are effective, others cannot have models but are constructed independently of them, while there are some which appear feasible in models, but when they have begun to increase in size are impracticable, as we can observe in the following instance. A half-inch, inch, or inch and a half hole is bored with an auger. But if we should wish, in the same manner, to bore a hole a quarter of a foot in breadth, it is impracticable, while one of half a foot or more seems not even conceivable. 6. So too, in some models, it is seen how they appear practicable on the smallest scale and likewise on a larger. And so the Rhodians, in the same manner, deceived by the same reasoning, inflicted injury and insult on Diognetus. Therefore, when they saw the enemy stubbornly hostile, slavery threatening them because of the machine which had been built to take the city, and that they must look forward to the destruction of their state, they fell at the feet of Diognetus, begging him to come to the aid of the fatherland. He at first refused. 7. But after free-born maidens and young men came with the priest to implore him, he promised to do it on condition that if he took the machine it should be his property. When these terms had been agreed upon, he pierced the wall in the place where the machine was going to approach it, and ordered all to bring forth from public and private sources all the water, excrement, and filth, and to pour it in front of the wall through pipes projecting through this opening. After a great amount of water, filth, and excrement had been poured out during the night, on the next day the helepolis, moving up, before it could reach the wall, came to stop in the swamp made by the moisture, and could not be moved forwards, nor later even backwards. And so Demetrius, when he saw that he had been baffled by the wisdom of Diognetus, withdrew with his fleet. 8. Then the Rhodians, freed from the war by the cunning of Diognetus, thanked him publicly, and decorated him with all honours and distinctions. Diognetus brought that helepolis into the city, set it up in a public place, and put on it an inscription: Diognetus, out of the spoils of the enemy, dedicated this gift to the people. Therefore, in works of defence, not merely machines, but most of all, wise plans must be prepared. 9. Likewise at Chios, when the enemy had prepared storming bridges on their ships, the Chians by night carried out earth, sand, and stones into the sea before their walls. So, when the enemy on the next day tried to approach the walls, their ships grounded on the mound beneath the water, and could not approach the wall nor withdraw, but pierced with fire darts were burned there. Again, when Apollonia was again besieged, and the enemy were thinking, by digging mines, to make their way within the walls without exciting suspicion, and this was reported by scouts to the people of Apollonia, they were much disturbed and alarmed by the news, and having no plans for defence, they lost courage, because they could not learn either the time or the definite place where the enemy would come out. 10. But at this time Trypho, the Alexandrine architect, was there. He planned a number of countermines inside the walls, and extending them outside the wall beyond the range of arrows, hung up in all of them brazen vessels. The brazen vessels, hanging in one of these mines, which was in front of the mine of the enemy, began to ring from the strokes of their iron tools. So from this it was ascertained where the enemy, pushing their mines, thought to enter. The line being thus found out, he prepared kettles of hot water, pitch, human excrement, and sand heated to a glow. Then at night he pierced a number of holes, and pouring the mixture suddenly through them, killed all the enemy who were engaged in this work. 11. In the same manner, when Marseilles was being besieged, and they were pushing forward more than 30 mines, The people of Marseille, distrusting the entire moat in front of their wall, lowered it by digging it deeper. Thus all the mines found their outlet in the moat. In places where the moat could not be dug, they constructed, within the walls, a basin of enormous length and breadth, like a fish pond, in front of the place where the mines were being pushed, and filled it from wells and from the port, and so, when the passages of the mine were suddenly opened, the immense mass of water let in undermined the supports, and all who were within were overpowered by the mass of water and the caving in of the mines. 12. Again, when a rampart was being prepared against the wall in front of them, and the place were heaped up with felled trees and works placed there, by shooting at it with the ballistae red-hot iron bolts, they set the whole work on fire. And when a ram tortoise had approached to batter down the wall, they let down a noose, and when they had caught the ram with it, winding it over a drum by turning a capstan, having raised the head of the ram, they did not allow the wall to be touched, and finally they destroyed the entire machine by glowing fire darts and the blows of ballistae. Thus by such victory, not by machines but in opposition to the principle of machines, has the freedom of states been preserved by the cunning of architects. Such principles of machines as I could make clear, and as I thought most serviceable for times of peace and of war, I have explained in this book. In the 9 earlier books I have dealt with single topics and details, so that the entire work contains all the branches of architecture set forth in 10 books. Finis. End of the 10 books on architecture by Marcus Vitruvius Polio, translated by Morris Hickey Morgan.